Thank you, Sam. Good morning, everybody. I'm Petros Koumoutsakos. I'm the Herbert S. Vinokur Professor for Computing in Science and Engineering at Harvard University. And I have the pleasure to chair this exciting workshop. This workshop started as a coordination between the National Science Foundation and the National Academies of Science, Engineering, and Medicine. There was an ad hoc committee that was coordinated. It was essential to have actually the help and coordination of Sam and Michelle Schwalbe. They have been amazing. And so this panel put together, this ad hoc committee put together some speakers and some panels. And the goals of what we try to do is we try to explore what can AI do for mathematical reasoning. We see AI everywhere these days, from music composition to medicine and everything else in between. And so we're wanting to explore what is the state of the art of using AI for mathematical reasoning. What are the opportunities to advance research in this area? What are challenges and barriers to use AI for mathematical reasoning? And finally, what is the role of the stakeholders in advancing AI for mathematical reasoning? I'd like to stress that the workshop will be summarized in the proceedings that will be published in a few months. And again, with these few words, I'd like to introduce David and Dilma from the National Science Foundation. David Manderscheid is the Division Director for the Division of Mathematical Sciences at the NSF. David is also a professor in the Department of Mathematics at the University of Tennessee, and his research is in representation theory and its applications to number theory. He has held visiting appointments at the Institute for Advanced Study at Princeton, the Mathematical Sciences Research Institute in Berkeley, and the University of Paris. And Dilma da Silva is the director of the Division on Computing and Communication Foundations at the National Science Foundation. Dilma is also a professor of computer science and engineering at Texas A&M, and her research interests are in cloud computing, operating systems, distributed computing, high-end computing, and computer science education. David, this is over to you.
Thank you. And should I, maybe I'll share my slides here. Okay, let's try this again. And okay, I think we see my slides now. Is that correct? Is that good? Okay. Dilma and I are here. We're collaborating on this project, and we're the ones that funded, along with another division, this workshop because of our interest in this topic, our mutual interest. And I will start by saying that I'll just give a little introduction to the Division of Mathematical Sciences, because given the size of the audience, they may not be familiar to everyone. So DMS is a division within mathematical and physical sciences. We support research, and we're the primary supporter of research in the mathematical sciences. Almost 75% of research in mathematical sciences that receives federal support receives it from us. So mathematical knowledge, mathematical sciences impact on society, and then workforce initiatives are our three areas, topics I would point to. And the science we support is both theoretical mathematics, applied and computational mathematics, statistics, and the science workforce. We have our core programs, things like algebra and number theory, analysis, so topology, geometric analysis, applied math, and so on and so forth. We also have many partnerships and collaborations. And I think one that might be of interest to this group is on the mathematical foundations of deep learning. That's a collaboration we do with the Simons Foundation. We also have the Mathematical Sciences Institutes. One was already mentioned in my bio, two of them, in fact, the Institute for Advanced Study and the Mathematical Sciences Research Institute. now SL Math out in Berkeley. We're having a competition, I'll mention, fiscal year 25. The solicitation will be out soon for for renewal and new institutes, and AI might be, and its role in mathematics might be a topic there that I'll mention. And then, of course, workforce, bringing more people into the mathematical sciences. I'll be fairly brief here and just say our budget is $250 million, but most of that, 180 million, is going to individual researchers. What's our interest here? What's our interest here? AI is a priority at NSF. It's one of the 10 emerging industries that's funded under CHIPS and Science Act. I won't go into the details of that. But in particular, AI's applications to mathematics has really, in the last few years, taken off. And I'll just point to two things that are of interest to me. As a number theorist, I'm very interested in, it caught my attention rather, the liquid tensor project, bringing the work of Schulze, providing verification of some theorems that he wanted to more fully understand the proofs of. That he was a little cautious about the proofs of. And then another example I'll point to as a representation theorist is the work of Williamson on Kazhdan-Lustig polynomials. So using Google's DeepMind to generate conjectures. So mathematics is a verification tool, AI is a verification tool, and AI also as a means to generate new mathematics and conjectures. And this interest is both at the level of research and education. One of the things that Dilma and I are funding this year, we sent out a Dear Colleague letter asking for applications, are looking for REU sites, research experiences for undergraduates around math and AI, the formal verification and theorem proving. And we see a real potential here to transform the way we do mathematics and to have a substantial impact. But really, the purpose of this workshop and why we're here is for you to tell us, what do you see as the emerging areas? I mean, you saw Petros showed you a screen earlier on the topics. What are the emerging areas? What should NSF be funding? What's the role of mathematics, AI in mathematics, and mathematics in AI? That virtuous cycle, I should say. So that's a very brief. I want to give some time to Dilma, but I look forward to hearing the remarks in this workshop, and I'll turn it over to Dilma at this point. So maybe I'll stop my share and turn it to Dilma.
And I'm going to try to see if my sharing is going to work. No, I'm still trying. Sorry. Let me see. I'll try something different. Let me see if I share the. Oh, is that working at all?
Yes.
Good? Yes, finally. Yay. Oh, thank you. So hi, everyone. I'm Dilma da Silva. I am from the Computing and Communication Foundations at the Directorate of Computer Information Science and Engineering. But I'm also speaking in terms of our colleagues in IIS, that's the Information and Intelligence Systems, part of SAIS. So in terms of a little view of SAIS. So SAIS, like David said, that the DMS funds a lot of the math research. NSF funds 80% of the federally funded CS in the academic institutions in the United States. And, essentially it's around $1 billion is our budget. And, roughly you can think that the budget for CCF, the Communication and Computing Foundations, and IIS, Information Intelligence Systems, is kind of like roughly half of that. So for SAIS, we see that our portfolio right now is really trying to focus mainly in three things. One of them is what happens with computing and enabling computing systems when we can't count on the fabrication just getting things that are faster and faster. There's a lot of roadblocks in getting our computing systems to be sustainable, efficient, and all of that. And in that space, I wanted to emphasize that we do invest on formal methods and verification of hardware and software. And that part of our community, I think, would benefit a lot of interacting with the people in this workshop. So that's one touch point that we value a lot. Another touch point is AI. We do have a large portfolio in artificial intelligence in general. We are one of the players on AI institutes, NSF has, I think right now we have, I lost count, I think it's 28 institutes. I know that we just announced earlier this month, 7 new institutes. So AI is, for NSF, one of the areas, and for SAIS, and also, of course, MPS, mathematical and physical systems. And another angle that we consider very important is to be looking at the social technical impact of our computing systems. So in this portfolio, which we look at SAIS portfolio, we see that the investments on foundations on how AI can be used for mathematics can really feed into many of these different spaces. So we are very excited about it. And when we now look a little differently and look at NSF big priorities, there are currently supporting emerging industries, supporting a resilient planet, creating opportunities everywhere, and enabling meaningful, impactful research infrastructure. We also see the conversation that is going, the upcoming report for this workshop, as feeding many parts of this. Certainly the resilient planet, because we do think that the way of advancing how we use AI to advance mathematics will not only advance mathematics, but the interactions, the tools can also help us to have safer systems in general. And in terms of creating opportunities everywhere, let me do a little bit of marketing and DMS, so SAIS and DMS. We recently released an Expand Tripods call. So Tripods is the Principles of Data Science program that DMS and CCF have been working on, and we have funded, a few institutes. And now we have a call to try to get people who have not been involved in that area, researchers from our 2 institutions, to be able to partner with the researchers in institute. And we give, funding for there is funding for the people in the R2 institutions, and also some funding on the existing institutes that we add to enable that. And that theme of getting people to work together is something that David and I are paying attention a lot. So I think I will stop here and try to stop sharing and just ending that both David and I, as we look at the whole process and NSF doing the budget for fiscal year 25 and everything, we do see a lot of connections into the elements that you're discussing in the program and our bigger vision for GMS and CCF. Finally, CCF is the foundation's home for computer science in SAIS. And therefore, I just want to emphasize that we really appreciate the work that is going on this workshop. And then we hope that from this workshop, David and I will learn more ways to get the foundational computer science people and GMS people to work together and solve more problems together. David, if I forgot anything that we should have said, please add. Otherwise, I'm done.
Oh, that was perfect, Dilma. Complimented my talk very well. Thank you.
Thank you very much.
And I think it's time to move on to the next session, which is our session 1, state of the art of using AI to assist mathematical reasoning. And we'll be doing a discussion on the overview and grand vision. And Brendan, I'll pass it over to you.
Thank you very much. My name is Brendan Hassett, and I'm a professor of mathematics at Brown University. Let me introduce the 2 presenters that will be kicking off this session. So first, Moshe Vardi is University Professor and Karen Ostrom-George Distinguished Service Professor in Computational Engineering at Rice University. He's leading an initiative on technology, culture, and society, and his interests focus on automatic reasoning, which is a branch of artificial intelligence with broad applications to computer science, including machine learning, database theory, computational complexity theory, and knowledge and multi-agent systems, computer-aided verification, and teaching logic across the curriculum. Our second presenter will be Jordi Williamson, who is the director of the Sydney Mathematical Research Institute and professor of mathematics at the University of Sydney. His research interests are in algebraic geometry and representation theory, and the richness and complexity contained in questions which need extremely sophisticated techniques from many fields, including algebraic geometry, Hodge theory, higher category theory, to resolve these important problems is quite extraordinary. So let me hand the baton to Moshe. So Moshe, the floor is yours.
We do the magical thing. Okay. And present and we are in business. So not yet. Okay. So it's a little presumptuous to give a talk called Grand Vision, but I'll give it a try nevertheless. And I will try to show that the quest for automated mathematical reasoning is a very old quest. We're talking about the newest incarnation of it, but it's been with us for a long time. So let's go back to the very beginning of mathematical reasoning. And for that, we have to go to the Thales of Miletus in the 7th century BC, where he proved the beautiful theorem that if you have a semicircle, then every angle that is inscribed inside the semicircle is a right angle. And he gave for this a deductive proof. A deductive proof is an amazing object because it's some people call it the high road to truth, because it's an airtight argument. Once you have a proof and everybody looks at it, say, yeah, this is a proof, the discussion is over. We have a proof. So this is the beginning of mathematical reasoning. And the Greeks also went a few hundred years later, and Aristotle studied reasoning per se. So Aristotle in his book Organon gave us the syllogisms, which are forms of reasoning. All humans are mortal, all Greeks are human, therefore all Greeks are mortal. And notice I can change this and tell you that all Bujums are Slavy, all Tovs are Bujums, therefore all Tovs are Slavy. And you must recognize that this is a valid inference, even though you have never seen a Bujum and you don't know what is a Tov, you have no idea why they are Slavy. Truths come out of form. That's why we talk about formal logic. Okay, so this is another huge step in mathematical reasoning for getting formulas. The Greeks also gave us paradoxes, and the most famous paradox of all of them is so-called the liar's paradox. Epimenimides, who said all Cretans are liars. The sharp way to make it really a paradox is due to Eubulides a bit later, who said this sentence is false. And is this sentence true? If it's true, it's false. If it's false, it's true. That's what gives the paradox. An important feature of this sentence, it refers to itself, self-reference. And we will see the self-reference will be a theme that will come again and again and again. Now we're going to jump from the Greeks, we're going to jump to Leibniz, who took this idea of automated reasoning to a whole new level. And Leibniz dreamed of having a mathematical language. We call it lingua characteristica universalis, in which all human knowledge can be expressed. And furthermore, there will be calculational rules, calculus ratio sinator, carried out by machine to drive all logical relationships. Famous quote, calculemos, he said, we don't need any more, we don't need philosophers. We can eliminate all philosophical disputes by computation, calculation. Leibniz dream did not go far enough. He was not able to carry it forward, but we're going to jump from Leibniz and we'll find George Boole, who takes not Leibniz's dream in a full, but he focuses on what we call the Boolean logic, just propositional logic. He goes to the syllogism, and he do algebraization of the syllogism. He realized that you can look at the syllogism and treat them algebraically. For example, a logical AND can be viewed as a product. A logical OR can be viewed as a sum. And that's how we get, this gives rise to Boolean logics, Boolean algebras. And what you see here is a picture from 2017. I'm visiting Ireland, and I'm holding here Boole's personal copy of his own book in my own bare hands. It was so exciting, I didn't wash my hands for a week after that. I touched Boole's copy of his own book. One of the things we got out of Boole treatment is we are going to see in a minute. We're going to think about it computationally, but we'll come back to it in a minute. But the other thing that happens in the 19th century is that there is kind of a reversal. If you look prior to that, then geometry is the queen of mathematics because it's a logically perfect science, deductive science, going all the way back to, I mean, essentially, when you learn in high school geometry, you still learn Euclid's element. And calculus was a bunch of recipes and told us, well, take divide the x by arbitrarily small x by arbitrarily small y, and it magically gave you some results. And then in the 19th century, we had a bit of a reversal because people discovered that there's nothing sacrosanct about Euclidean geometry. There are non-Euclidean geometries. And finally, calculus was formalized in terms of limits. But this formalization in terms of limits created a problem because limits are about infinity. Infinity is dangerous. So the question now arose now, what is a rigorous proof? I said a proof is an airtight argument. Well, can we be more precise about what is a proof? And then Cantor studies infinity, and he proves that there are infinitely many distinct infinities, and of course, he proves again your self-reference. And now you have a huge debate among mathematicians about the infinite. Is it okay to use the infinite in mathematics? Cantor used it. Gauss and Kronecker were against it. Hilbert was a huge fan of the infinite. So where does the infinite lie? And this raises the question again, what is a rigorous proof? And so in an attempt to answer that question, Frege wrote in 1879, a small book, Begriffsschrift, in which he tried to answer a more fundamental question, what is the language of mathematics? And he came up with logic is the foundation of mathematics. This is called logicism. And he basically said, we have a universal language for mathematics. It's about mathematical objects. If we do number theory, the objects are numbers, relationship between them, predicate, operations on them, functions, Boolean operation or logical operation, and an or not, and quantifier, which is introduced just in the late, around the time 1870s, quantifier were introduced for all and for some. And now we can go back to the syllogism and we can formalize them. We can write formulas. Instead of saying all men are mortal, it means for all x, if x is a man, x is mortal. And we write it now inverted x, inverted ax for all x, man of x implies mortal of x. So this is Frege's book. And in 1902, he's going to publish, he's publishing a second book. And it turns out that the crux of the next book is that mathematics can be based on set theory. And then he gets a letter from Russell, and Russell pointed out that Frege's logical framework is inconsistent. There are paradoxes inside Frege's system because is the collection of all sets do not include themselves as member, is it a set or not a set? If it's not a set, then it is a set. If it's a set, it's not a set. Again, it's a large paradox. Again, Hippolyte has spoken from his grave, and Russell, after 2,000 years, and Russell has launched what became known as Grundlagenkrisis, the foundational crisis in mathematics. So suddenly, the very heart of mathematics lies a paradox. Now, Hilbert, which was the reigning mathematician of the time, was shaken by that. But before that, Russell thought he can solve the problem. And together with Alfred North Whitehead, they published Principia Mathematica, which took them 10 years, 3 volumes, 2,000 pages, a systematic derivation of mathematics for logic, avoiding the obvious paradoxes. Russell said after that he couldn't do any more logic. He could not, it was such a strain on him. And for a little while, it seems maybe the crisis has been resolved. But then people realize, wait a minute, Frege had a small book and it had a paradox. Now Russell has 2,000 pages. How many paradoxes are lying in these 2,000 pages? So we are not, the problem arose, but we are now entering World War I. So Hilbert had to wait until after World War I, where he basically says this situation is unacceptable. We have to put mathematics on solid foundation. We have to prove mathematically that mathematics is consistent. It has no paradoxes. But he got more ambitious. All mathematical questions can be answered. If sometimes you prove negative result, you prove there is no answer, but that's your answer. And the automation of reasoning. Remember the idea that went back to Leibniz. Now the same thing Hilbert says. Mathematics has to be decidable. There has to be a mechanical way to decide whether the given mathematical statement is true or false. And the key idea that Hilbert puts on the table, that until this point, proofs floated somehow, proofs were used by a mathematician, but they were not studied by a mathematician. And Hilbert says, we have to study proof theory. We have to study proofs as mathematical objects. Now, within a few years, Hilbert's program collapsed completely. Gödel proved the incompleteness theorem. So there are sentences in number theory whose truth or falsity cannot be resolved using the axiom of arithmetic number theory. In fact, you cannot prove the consistency of number theory in number theory. And a few years later, Church and Turing would prove that first order logic is undecidable. Whether a sentence in first order logic is true or not cannot be decided by an algorithm. This is what Turing machines and recursive function were introduced to define computability. So the true sentences are innumerable. That is, we can pursue the truth. There is an algorithm that spits out all the valid sentences. But until a sentence has been printed, we don't know whether true or false. And so we can wait billion years, we'll never know whether something is true or false. And finally, this is not less celebrated result, but I think it's really important in this story. It's a definition by Cook and Recco from 1979. What does it mean to have a proof system? This question was not fully resolved by Church, Turing, Kleene, etc. And Cook and Recco define it. They say, suppose you have an alphabet sigma, and you have a set of words in sigma star. So these are your theorems. What is a proof system? A proof system is an algorithm over 2 alphabets, sigma star and auxiliary alphabet delta. And you're given a pair, UV, and you want to know whether U is a theorem, is a member of L, and it's a member of L if and only if there is some V in delta star such that AUV equal 1. So think of V as the proof that U is in L. And that proof has to be checked by an algorithm. So the answer that comes out, and finally we got the answer in 1979, what is a rigorous proof? A rigorous proof is a proof that can be checked algorithmically. So if proofs are the very heart of mathematics, algorithms are at the very heart of mathematics. Proofs are algorithmic objects. Now, remember Boole. Well, Boole didn't quite say it, but one thing that comes out of Boole is so-called the Boolean satisfiability problem. So that is, you're given an expression using what we call Boolean variables. So each variable here, x1, 2, 3, stands for 0 or 1. And the operation are the wedge is an AND, and the V is an OR, and the squiggle is not. So this is not x1 or x2 or x3, and not x2 or not x3 or x4, and x3 or x1 or x4. can you make it evaluate to 1? In this case, it's not very hard to see that if I choose x1 and x2 to be 0 and x3 and x4 to be 1, this will evaluate to 1. You have 4 variables, you have 2 to the 4, 16 possibilities, try them all out, easy to solve. But suppose we don't have 4 variables, but 40 variables, maybe 40,000 variables, or how about 4 million variables? So this, this is not automating all of mathematics, but it's automating in some sense, some of the most fundamental part of what is proof, which is just Boolean reasoning. Can we mechanize that? And this problem already popped out on people's horizon in the 19th century. Williamson and Gibbons. I've given much attention to lessening both the manual and the mental labor of the process. And he actually designed a machine that can handle 4 propositions called logical piano. The next quote is one of the most amazing quotes in mathematics I've ever seen. Ernest Schroeder, a bit after Gibbons, getting a handle on the consequence of any premises, logical premises, or at least the fastest method for obtaining these consequences seems to be one of the noblest, if not the ultimate goal of mathematics and logic. So Ernest Schroeder tells us that automating mathematical reasoning is the ultimate goal of mathematics and logic. Except we learn about 100 years later, in the early 70s, we learned that this is NP complete, even just Boolean satisfiability, which means that it's unlikely we can do it efficiently. But people didn't give up, they continue to be SAS solver. And we have the SAT revolution started in the mid-90s, two tools, important tool, GRASP and SHAF in 1996 and 2001. And today, modern SAS solvers are called CDCL, conflict-driven closed learning, and they have a combination of heuristic. They're based on backtracking search, but don't just backtrack means you fail. You start to go up the search tree, jump up the search tree. If you got a failure in the search tree, learn from your mistakes, and so on and so forth. I can talk at length about this. I think calling it CDCL was a huge marketing mistake. They should have called it deep solving. That would have been much better choice. And today we solve problems with millions of variables. When I was a graduate student, nobody could think that you could solve more than 100 variables. And this is a 10-year-old slide, but it's still impressive. And this is a colleague of mine who took 10 years of such solvers and ran them on one machine, on one benchmark. And the SAS solver I mentioned, GRASP, took 800 seconds to solve that benchmark. And then by 2012, Glucose 2.1 solved the same benchmark in 1 second. So we have seen over a decade about 3 orders of magnitude improvement. And this improvement has continued so much so that people talk about this mysterious Moore's law for SAS solver. SAS solver continue to improve. And if you kind of think, well, this is just propositional reasoning, this is not really what we mean by mathematical reasoning, here is a beautiful mathematical problem. Pythagorean triple is x, y, and z, three natural number x, y, and z, such as x squared plus y squared equals z squared. The Pythagorean triple coloring problem is, can you split the positive integers into red and blue colors, split it in two, such that there is no monochromatic Pythagorean triple. No Pythagorean triple, all the numbers will have the same color. That was answered in the negative by Euler, Kuhlmann, and Marek in 2016. But they didn't come up with a beautiful deductive proof. They reduced it to SAT, and they used what they call brute force science to show that it failed up to some large number. Of course, we couldn't try all numbers, but it showed that for a large enough set of numbers, this already failed. The proof was 200 terabytes long. They said this is the largest proof ever, but the proof was found and checked algorithmically. So let me wrap up. Partly in this grand vision, I try to show you that the quest for automatic mathematical reasoning is at the heart of mathematics and computer science. We went back all the way to Leibniz. We've seen that there's a huge progress in the area. I talk here about Boolean reasoning, but there is also huge progress in automated deduction, in proof assistant, from one side, from computer science, formal verification that Gilma mentioned was a huge driver. Today, the biggest automated reasoning group sits at Amazon, at AWS, Amazon Web Services. There is a largest group ever in formal verification. And mathematicians have launched projects that try to formalize mathematics. They say there are some proofs that are just too complicated to trust that humans can actually evaluate, check the proof. So we have to formalize this proof. So huge progress. And now we have this deep learning and large language model. And I think it's the question is, what role can they play? In my area, I've seen a graph neural network being used for such solving. But Jordi will talk about deep learning for developing mathematical intuition. So I look forward to exciting 3 days of this workshop. Thank you very much.
Thank you, Moshe. So, I'd like to ask one quick question before Jordi starts. So can you give an example, a concrete example of how deep learning have changed your approach to these set problems? Is there a specific type of problem that is particularly amenable to these new techniques?
So people have actually built tools for such solving. They're based on graph neural network, which are a particular type of neural networks that run on we are familiar with deep learning model that run on pictures or sentences. This run on graph. And they have shown to be effective, and it's a huge mystery. So right now, part of what I'm trying to do is try to understand this NP-complete problem. What is going on? I mean, I started this, in fact, looking at TSP some years ago. And my first approach was, let's show that deep learning people that follow themselves, and deep learning will totally fail on traveling salesman problem. And it was amazingly effective, which is total mystery, okay? NP-complete, we thought that there's no way we can do that. But it was quite successful, and we need to understand it. So we said that the relationship is going to be two-way. Partly is also trying to use mathematics to understand. In this case, I want to use mathematics to understand how deep learning helps mathematical reasoning. So we are kind of, it's becoming a bit convoluted. We're looking at ourselves. So look, it's a bit navel gazing here.
Okay, well, we'll have more discussion in a moment, but I wanted to hand the baton to Jordi Williamson. Those of you that are following using Slido, please send questions. We'd like to have some interaction between the audience and the presenters. And so I will read questions that come through Slido. So please share your questions about the scientific content and its implications. I forgot to mention one important part of Jordi Williamson's bio. And so he's been working with Google DeepMind since 2020 on the interactions between mathematics and deep learning. And so he has a unique vantage point to discuss how problems in traditional core mathematics will be approached in new and innovative ways using these modern techniques. So Jordi, I'm gonna hand the baton over to you.
Thank you very much, Brendan. Okay, I hope you can see me now, and I hope you can hear me. Okay, great. Thank you very much for the invitation to speak to you all today. So I think Moshe's title from last talk, he suggested deep learning and intuition. So that's probably a really good summary of what I'm talking about today. So I'm talking about how does one use deep learning to guide mathematical proof at a very, or reasoning at a very high level. But I also think it's extremely important to have some basic picture of what deep learning is. And so I'll spend some time on that. So I'll start with a brief introduction. So this is a fantastic paper of Alan Turing from 1948, Intelligent Machinery. So this is one of the first papers that suggested the possibility of AI. It's a research report. And I find it really interesting that he provided 5 possible avenues for experimentation with AI on human activities, namely games, learning of languages, translation of languages, and mathematics, cryptography and mathematics. So mathematics has kind of been there as a litmus test for AI from the very beginning. And I think it's really important to remember that reasoning is still a major obstacle in current AI. And thus one can see the question of, can deep learning contribute in a meaningful way to mathematical reasoning as an extremely important litmus test for what modern AI can do. I also want to very briefly mention, I think it's very important to remember that we have, I feel somewhat torn when thinking about this stuff, because I think that the ideas of deep learning are extremely beautiful, and I'm using it on a subject I love, but it also has the potential to transform this subject, perhaps to provide something very different. And so I think it's really important to remember that we can make deliberate decisions about what we do, and that I think that mathematicians and computer scientists have an incredibly important role to play in this current conversation around AI and what we want from it. And I think there was this Fields Medal Symposium last year, which has very interesting discussions around what we want from automation. So if you're interested, please have a look at that. Okay, so where does mathematical understanding come from? There's this beautiful quote of Claire Voisin from the notices last year. So she's talking about the mathematical process, and she says there's the monastic introverted period where we are just contemplating the ocean of our ignorance, but then suddenly something happens. The monk becomes busy and excited in a hurry to look more closely at the detail. So I think it's a fascinating question where that suddenly something comes from. And I think that there's a tendency amongst people who are not doing research mathematics every day to kind of conceive of a mathematical argument as being some kind of formal proof through a proof landscape. But I just want to emphasize that the sources of mathematical understanding, the kind of steering process of the reasoning process for the research mathematician, are incredibly diverse. So, for example, we're guided by intuition, geometric intuition, perhaps physical intuition. We're also guided by our understanding of proofs, and proofs can have many different forms. So we might have a proof without words. There's many proofs of simple statements which don't involve a single kind of word, and in contrast to that, you have like 200 terabyte SAT proofs, as mentioned in Moshe's talk. Notation plays a big role. Correct notation can guide us in the right direction. Analogy is something that I'm absolutely fascinated by. We begin to have a sense of what, for example, a vector space is by our experience with the three-dimensional world, and yet we're able to use that intuition to explore infinite dimensional spaces, for example, in functional analysis. Computation plays an extremely important role, as do heuristics. So what I'm basically trying to say in this talk is that deep learning can aid the more intuitive parts of the mathematical process, so the parts on the left of this diagram. So as Brendan said, I've been working with DeepMind for the last 3 years on mathematics and deep learning, and I just want to give you some picture of what it's like to work with deep learning as a pure mathematician. So in order to do this, I want to briefly discuss deep learning. So there'll be several other talks on this. And so this is some kind of just introduction. So I'm assuming that some good percentage of the audience has never seen deep learning or doesn't have much of a mental conception of what it is. And then I want to give some brief advice for people interested in working on this stuff. And then I want to discuss one example in some depth, as I think it's important at the genesis of this extremely interesting subject to be very familiar with examples. So here's a crash course, about 7-minute crash course into in deep learning. So I think it's best to think, at least as a first approximation, of a neural net as a type of function approximator. So an example of such a function we might want to approximate is the function that takes in the pixel values of an image and outputs a probability as to whether this is an image of a tiger or not. So this is a function which we can posit to exist. It seems to exist in our brains, and we can ask, can we approximate such a function in some meaningful way on a computer? Another example of such a function is a function which takes an incomplete sentence and then outputs a probability distribution on the next word. So these are very close to the type of functions that appear in large language models. So how do we do this function approximation with a neural net? So we build a neural net. So here's a very crude picture of one. So essentially what we do is we combine linear algebra or affine linear algebra with nonlinearities. So this is a very crude picture of a neural net. We start in some very high dimensional space typically, and then we do a linear or affine linear map to another space, and then we apply this ReLU operation. So this is a nonlinearity which sets all values to be zero, all negative values to be zero, and keeps all positive values. So this is one possible nonlinearity, and many other choices are possible. And then we continue. And so this is a very crude imitation of what we suspect might happen in the brain. So this is why it's called the neural net. And typically, so you can think of this as describing an enormous space of possible functions. And then we try to find a, so we have a target function, or we might not have the target function, but we might have a number of values of the target function. And we approximate this target function via gradient descent on this big space of possible functions. Okay. So this is this lovely site on the internet called the TensorFlow Playground, where you can play with these ideas. So here's a simple run of this. So on the right, we have our training data set, which is this spiral, and we have a classification task. So we want to classify the nodes of this spiral as to whether they're orange or blue. So we want to train a function which is basically negative on the orange part of the spiral and blue on the sorry, and one on the, or positive on the blue. And here we see it starting to train. Okay. So as we're training, we're wiggling the weights, which are the which are indicated by the darkness of these. So these are, so for example, blue here means negative weights and orange means positive weights. So these are slowly changing, and on the right you can see our function slowly changing. So we're moving in this space of all possible functions and slowly approximating the function that we're aiming for. Okay, and so you can see many things here that are kind of typical in training. So this process of gradient update is known as training. So the first thing is that this is very stochastic. So we initialize from some random initialization scheme, and also the steps of gradient descent involve some randomness. So if I did this 10 times, I'd get 10 different answers each time. And also you see, for example, it's possible during training to get worse, better. So this is a very complicated optimization problem, which by some miracle seems to work in many different situations. So here we have our input, here is our output, which is our final. And then these are called the hidden layers in the middle. And I just want to show you a little, so here's a little illustration of what happens in these hidden layers. So you can see that it's trying to move space around so that, for example, the green points here are located in the region of space that might be more easily accessible by, for example, a linear function. So both of these sites, this is Kapathi's ConvNet demo. It's also the TensorFlow Playground, great to play with to get some feeling, some intuitive feeling of what's going on in these networks. So as a mathematician, we're used to a certain type of function, and I think it's really important to remember that deep learning is designed to work on very different functions to the ones that I grew up with in my mathematical education. So something like trying to decide whether a photo is an image of a tiger or not is a rather different function to the functions that I'm used to. And so these are some very simple heuristics, which I've kind of slowly learned over the last couple of years. So deep learning is is best when the input dimension is very high. So if you have a function in the small dimensional space, there's very classical approximation methods which will potentially work better. The function is on the unit cube. So if we use the brain analogy, in our brains, we hope that voltage stays in a particular region, a very small bounded region. Yeah. And it's the same in neural nets. You would like the values that show up to be, for example, between 0 and 1. And also, coordinates have low symbolic content. In other words, the function is reasonably noise stable. If you think about something like recognizing a tiger, this is a very noise stable function. So number 3 comes with a big asterisk. There are situations in which neural nets can learn very subtle things, but I think it's a first approximation. It's a good one. And one of the incredible things about deep neural nets is that they appear to overcome in certain situations the curse of dimensionality, which is basically that if I have a function on a very high dimensional vector space, I need an unreasonable number of its values in order to approximate it in any classical setting. Okay, so here's a picture of just kind of geometric picture of training that I like to have in mind. So imagine that we break up space into various polytopic regions. So this is what I've tried to depict here. And now you can imagine these regions moving and us learning a linear function on each of these regions. And this is a picture of what happens during training. So these regions move around, the linear functions on these regions also move. And so it's a bit like incredibly high level, like very complicated linear regression in some sense, like it's. Okay, so just some brief advice for mathematicians that are interested in this stuff. So neural networks are extremely difficult to interpret. So I think in industry, if you have a result like our model gets 98% accuracy on problem X, that is wonderful. However, as mathematicians, if we're after understanding, this is typically not useful. So I've definitely had this situation several times where I have a neural net, it's extremely accurately predicting an answer to a question that I care about, but somehow we need more. Another very important point is that one should expect difficulties from an engineering point of view when experimenting with neural networks. So I gave the simplest possible architecture before of a neural network, but typically problems need more complicated architectures. For example, graph neural networks that Moshe mentioned, transformers, convolutional neural nets, etc. And also within these architectures, there's incredibly important and subtle choices. And so, yeah, I find it disconcerting. Typically, you know, when I'm playing with this stuff, sometimes something doesn't work and I'm not sure if it's just a bad idea or if my implementation is at fault. I think the computer scientists in the audience will be much more familiar with this than the mathematicians. So there's a lot of hype. So I think that there's just incredibly beautiful ideas in this world, but one has to be careful of the hype machine. So for example, when I entered this world, I just thought that this vanilla neural net structure can learn any function. I mean, learn any function very accurately, very fast, very reliably. And I think that this is in some sense the fault of this hype machine. Okay, and the language, you know, learning, attention, hallucination, etc. It's very suggestive, but sometimes it's a little bit too suggestive. And I would really suggest working with experts in deep learning. So there's a great possibility for interdisciplinary work here. Interdisciplinary work is challenging, but the rewards are worth it. Okay, so I just want to discuss one example from my own work. Also, we have these talks discussing this. So this is all amazing work, Charton, Wagner, and Gomez-Serrano. It's really amazing examples of deep learning in maths. So this is one example. So I'll just go over this briefly. So this is a problem in representation theory. So we start off with a pair of permutations, for example, of a 20-element set. So we have a pair of permutations, so there's an enormous number of such pairs, and we can associate to these two objects. So it doesn't really matter what these objects are. So one's a Bruchar graph, it's a directed acyclic graph. The other one is a Koumoutsakos polynomial, which is a polynomial in one variable in Q. And in some sense, the Bruchar graph is a very complicated object. It's a very big, complicated graph, but it's somehow easy to associate to X and Y. Koumoutsakos polynomial is a very simple object, but its computation is very complicated, and there's many mysteries that are still present in these polynomials. So there's a conjecture that you can go from this Bruchar graph, it's a 40-year-old conjecture, to Koumoutsakos polynomials. And this is what we attempted to attack with deep learning. So this is a classic situation where we have some kind of complicated object and we want to distill some basic judgment out of this object. So that's the conjecture. We trained a graph neural net to make this prediction, and it did so extremely accurately after a few days of training. So this is a typical situation, I think, that we'll encounter more and more, that we have a neural net that very accurately predicts something, but the difficulty is distilling understanding out of the neural net. And so something that I found fascinating in this project, which it took us a while to, so very early on, we had a very accurate neural net, but we didn't know how to distill some kind of understanding out of it. And we noticed that there's a labeling of the edges, which we don't give to the network, which somehow the network appears to know. So this is a picture. So I won't explain what this picture means, but one can stare at this picture and see there's something very interesting going on. So just as an example, here's something that I meant to stare at and I meant to distill a polynomial out of. And the network tells me that the thicker arrows are more important than the thinner arrows. And then when I started staring at these pictures, you start to see certain hypercube structures emerging. So you can kind of see a concept emerging, some kind of possibility of proof emerging by looking at what the neural net is doing. And after a lot of work and thought, this led to a conjecture, which would solve this conjecture from 40-year-old conjecture. And we've proved it in an important special case. And also since our work, there's been a number of works in combinatorics which have taken this formula in various directions. So I think it's a very interesting kind of new formula which arose from deep learning. Okay, so thank you very much. So there's the work that I've discussed here appeared in an article in Nature where we also discussed this saliency method as a way of gaining intuition. And also there's a survey article which I attempted to write, which gives a lot more detail on what I was discussing concerning basics of deep learning and mathematics. Thank you very much.
Thank you, Jordi. So I have a question that was addressed to both of you, and maybe I'll let Jordi answer it and then Moshe. So what do you think about the role of mathematicians' intuition? So is deep learning a way of replacing the intuitive process or enhancing the role of intuition in addressing mathematical problems? So I'm curious to hear both of your thoughts on this.
So thanks a lot, Brendan. So I think that what I was trying to get at in the slide about where does understanding come from is that as mathematicians, we get understanding from several axes, many axes, I think. And I really can see deep learning as providing another axis as a source of intuition. And I think as with any tool, the more we use this, the more proficient we will get at accessing this new access of information.
Moshe?
What I like about Jordi's answer is that it takes out the fear element. There is this kind of, we are now living we are reliving Frankenstein, so to speak, right? The monster the genie is out of the bottle and the AI has awakened, it's going to take over the world and going to lead the extinction. and you start thinking about the deep learning mathematics, so well, we won't need mathematicians anymore. Everybody will be replaced by deep learning. And at this point, who knows? In 1,000 years, I have no idea what's going to happen. In 100 years, I have no idea what will happen. But right now, a lot of what we're hearing is fear mongering. And I think I like Jordy's approach is constructive. We'll have another tool for mathematicians. I mean, as we had, a number of theory, people discover, let's run an experiment. And they do not experiment they don't prove the theorem, but they provide the mathematician with an intuition. So deep learning, if we need to work, I mean, we had an example, we need to work harder and to try to make it into a tool that provide intuition. It's another tool for mathematicians. So I think that, I have to say, from my perspective as a computer scientist, I was trained as a theoretician. So the only assertions I would make were assertions that were based on, here is a proof. And when it comes to computational challenging problem, we have, NP versus NP, it's still an open problem. So we're actually becoming more experimentalist there, because that's the only way right now for many of the problems we're going to get some answers. So we're in the, we build tools, especially computer science, we build tools, but we use tools to build tools, and this gives us another tool. So having another tool should be an exciting development.
So another question for both of you, maybe Moshe can start. So take an example of Fermat's last theorem, or one of the crowning achievements of core mathematics. How do these different approaches, SAT solvers, formal methods, machine learning, what are they going to do for our understanding of these great results? Will we get new proofs? Will we get new understanding of why they're true? Will we get more easily explained principles as to what's behind them? So could you discuss that briefly?
I think the honest answer is we have no idea. we have a new shiny tool, and we're kind of trying to see what it can do. And we've heard from Jordy about some applications, what we can do. We heard about we have the whole thing where we have starting actually probably with the four-color theorem, with the rising of what we call computational proofs, which are for mathematicians, they're very unsatisfying. Hamming said the goal of a proof is the intuition. And Claire was in, this magical idea, this insight that pops into your head suddenly, and you suddenly, it's like the screen that covering Platonian space has been torn, and you're peeking into Platonian space suddenly, and you're seeing the truth there. And that's what, as mathematician, we expect to have. And this is what Fermat's last theorem, the proof of Andrew Miles and Taylor ultimately was based on this kind of magical view. I mean, Saharon Shelach is one of the most prominent logicians in the world in Israel. And a colleague once described him to me as someone whose head is in Platonian space, and he can see things that nobody else can see. And but we have like four-color theorem, the Poincare conjecture. We have proofs that have just huge computational proofs. And maybe one thing that imagine if somebody would now take, for example, go back to Fermat's theorem and try to take this. I think the latest, after the reduced number of cases, is still a reduction to something like 600, 700 cases, which for us is just, there's no insight there. It's a big blob. Maybe we can uncover some mathematical structure in this big computational proof. And so it's conceivable to me that actually the places where we lack the intuition, that we just did really brute force science, some intuition will pop out of it if we learn how to use this tool to develop intuition. So to me, that possibility is just, I find it incredibly exciting.
Thanks. Jordy, do you want to weigh in?
Yeah, sure. So one thing that I think is extremely interesting right at the moment is so I've been following, formal proof as an outsider for many years, and been, somewhat interested in SAT, again as an outsider. And I've always seen, so for example, computation, formal proof, machine learning as these kind of separate things. And I think that it's really fascinating at the moment that we're starting to see, for example, like there was this work on draft sketch prove, where a machine learning agent comes up with a possible statement, and then a SAT solver, as part of Isabel, tries to fill in a piece of the argument, resulting in a formal proof. So you have these three components all playing together. And the other thing that I think incredibly, so in my absolute soul, I'm a mathematician, so I really want understanding. I mean, I'm a particular type of mathematician that likes to live in the Platonic world that Moshe is discussing. So, and I find examples where some kind of human meaning comes out of neural nets extremely compelling. And I think that we've been, as a community, I think that up until recently, we've just kind of decided we'll never understand what's going on inside neural nets. But there has been work over the last kind of couple of years where you start to see something like concept formation in neural nets, which I find absolutely fascinating. So I think that one could imagine a time, and I don't think that time, it's possible that time is not so far away, where we actually we can actually distill a human comprehensible concept out of a neural net, which would be very exciting.
I mean, I think I'm intrigued by the possibility of turning neural nets on themselves, because right now what you get when you train a neural net, you end up with a big blob. And that blob does magical thing, but we have no understanding what's going on inside. And maybe we can take Jordi's idea of looking at complex combinatorial objects and try to distill some like simple polynomial out of them. Maybe we can get some insight on what's happening inside the neural net. So I mentioned to you, for example, that we built a graph neural network that did very good approximation of a traveling salesman problem. But it's a blob. Can we get insight out of the blob? What's going on? Why are we able? This is a computationally challenging problem. Why is the GNN so effective on it? We have no understanding. And so we might recursively be able to go in and use neural nets to build insights about neural nets.
So a question, I think I'll frame it for both of you. So if you take existing computational mechanisms like SAT solvers or computational tools that are used in representation theory or combinatorics, which do you think would be susceptible to neural network techniques, and which do you think will resist being attacked through these techniques? What are your general thoughts on this? Jordi, maybe you can go first.
Yeah, so of course I've been trying to think about this rather a lot, and I think that at the moment we have a few data points, but we don't yet have enough. So I think it's incredibly important to not be too guided by a sense of this will definitely work or not work on problem X. But I definitely think some kind of smoothness in the kind of learning landscape. So like in the example that I discussed, these graphs, I think that they're somewhat noise stable. So if you deleted some edges from them, probably the Cauchy analytic polynomial, even though it doesn't quite make sense, should still be the same. And it definitely seems to be the case that on these more noise stable problems, these techniques are easier to use. But I also should say that I'm kind of consistently surprised. And so my intuition for where this works and where it doesn't is still being formed.
Since SAT solvers are probably relatively sensitive to noise, Moshe, you have any thoughts on the same question? So,
my initial intuition was that there's no way that deep learning, these are such discrete problem and they are sensitive to any disturbance. You flip one variable, you flip the polarity of one variable, it changes the meaning of the whole thing. So, part of what we saw, going back to Fermat's theorem, was the key thing was really making a connection. It was not obvious at all going from number theory, going to kind of analytic number theory, and going to the continuum. I mean, this is Neumann used to complain about the discrete mathematics. He says it's continuum mathematics. We have all the powerful tools. So partly what we've been trying to do is to bridge between SAT, which is very discrete, Boolean, yes, no, and continuous mathematics. And so we developed a technique of mapping SAT formulas into polynomials, and then try to optimize this polynomial in a continuous space. And here we are using gradient descent. So what we've taken here from deep learning is the effectiveness of these new optimization tools. And now we kind of try to look at satisfiability coming from the continuous side, looking at gradient descent on the hypercube, on some complicated structure inside the hypercube. So right now, everything is open. There are lots of possibilities. Partly why this workshop was done, to get people excited and to float many ideas. Most of them will not work, but a few will be transformational, pun intended.
Thanks, Moshe. So one thing that you've both done in your research is you've bridged sort of narrow disciplinary confines and work with people from other silos. So what are the language gaps to doing that, and how have you managed to make those connections from the areas where you started work to the broader mathematical, computer science, logical world? So Moshe, maybe you can go first.
I remember the first time I gave a talk to physicists. This was before I came to RISE with IBM, and physicists I've given a talk explaining what I do. And I start talking about the graph. And then I saw the puzzled look on their face, because for them a graph was a picture of a function. That's a graph. And so you kind of have to remember that just basic words don't mean the same thing, and you need to think about what are the key terms I'm going to use. What am I assuming? Every time you have such a conversation, you have to go visit your assumption, because we always have assumption. What is the background knowledge? You have to question your assumptions, and if you don't know before you go, have a private conversation with someone, try to understand, okay, what, because the language is the key thing. What language are we going to use? That's the kind of thing, the key thing. Then there are different disciplines have different concerns. I remember trying to explain again at IBM to the lab director, who was a physicist, why P versus NP is such an important problem. And he says, but you guys believe that P is different than NP. And I said, yes, this is the prevailing wisdom. He said, why don't you just accept it and move on? If you have no evidence on the contrary, this is physics, accept it and move on. And I have to say, well, if we don't understand, if we don't have a proof, it means we don't understand it. And what we're seeking in, again, is the understanding. Okay. I mean, he was applied physicist, so for him, proof didn't mean too much, but understanding, he understood understanding. So you just have to be flexible in your thinking, and remember that we all got, after a while, we got trained into a narrow way of thinking. We need to reopen it to work with other people, other type of people.
Jordi?
Yeah, thanks. I think it's a really great question and an important question. So the two things that I think I would highlight is the time it takes. So I think when I started talking to the DeepMind researchers, it really took us about a year before we had a solid common language that we could speak. And this was, meeting every week, trying to get to the bottom of things every week. So, good interdisciplinary work really takes time. And the second thing that I think was kind of surprising to me is the difference in, like the issue of goal alignment. So, I really care about specific
value alignment.
Or yes,
it's a joke. Value alignment.
Yeah, so I was just kind of, I kind of, I've been thinking about problems in mathematics for so long. It's almost axiomatic that they're important, and it's a little bit similar to Moshe's story, where it's somewhat shocking when someone says to you, "But why do you care about the Riemann hypothesis?" like we just care about general methods for solving problems or something like this. So yeah, I think it's really important to be aware of that. Looking in the same direction and slowly developing that takes a lot of time. And it also means that now there's questions that I find extremely interesting that I was absolutely uninterested in before I began this work.
This is what Jordi just said. This is the key thing. If you work with someone and you're not absorbing, you're not changing how you look at the world, then you're not really talking to them. A real conversation, both sides have to come out different after they had this conversation.
So there are infinitely many logical questions, infinitely many mathematical problems. So how does the development of deep learning neural net techniques, how does it influence how you pick problems to think about, how you sort of query the space of problems? What are, of all the things that you could possibly ask for? Does it change how you think about the landscape of the questions that could be asked? Moshe, why don't you go first?
I would say not yet. I don't think we are there yet. It will change how I think about it. So how do we choose problems? Okay, I mean, the answer is sometimes they just pop the same magical insight, the same way that Claire describes so beautifully how suddenly this vision comes into your head. Suddenly a question comes to your head. What if? And what about that? I have not thought about this one. Just magically. Sometimes we live in a community, okay? And we talk to other people and we see the literature and questions come up from your conversation with colleagues, from you're seeing a new paper, and that gives you, that's open new questions. So I don't see yet deep learning as impacting it or in the same direction. I don't see necessarily how such solving would change the way mathematicians open problems. But if let's take deep solving and deep learning, if they become tools for the working mathematicians, then they will change how mathematicians think, because now they know I have a tool, I can use this tool. And the fact that knowing that you have a tool, they will change how you choose problems, because we all partly know that some problems are for example, Andrew Wiles spent 7 years working Fermat theorem. I wouldn't, because I know I had no chance. So part of choosing a problem is thinking, I think I have a chance of solving it. Otherwise, there are problems in mathematics that I'm not working on. They're interesting, P versus NP, and it's a fascinating problem. I'm not working on it right now because I don't have any idea of attack. But if you have more tools, then you have more ways to attack a problem. And that may change how we choose problems. So I don't know that we're there yet. We saw an inkling how deep solving can solve a mathematical problem, and people have tried to use analytic method to solve it, and they have not succeeded, and suddenly we can solve it. So there's a whole bunch of people now looking how can you use a deep solver to solve other kind of problems in mathematics. And Jordi's work will maybe give us a way how to use deep learning to propose intuition, to propose mathematical conjectures. Tools will change how we think about mathematics. Right now, we're in a we're building tools.
Thanks, Moshe. Jordi?
I basically totally agree. The tools change the discipline. The other thing that I think is extremely interesting and it's a focus of one of the sessions here is the amazing mathematical problems that actually come out of deep learning. And this will certainly change maths. And I think that there's an incredible richness in mathematical foundations of deep learning, and I'm really looking forward to that session.
So I have a question something that I just noticed. So Jordi has been working with Google, one of the current world's leading technology companies. Moshe spent many years at IBM as one of the world's leading technology companies, and you're both at institutions where we have access to people in many different fields. So how do we create an ecosystem where someone that isn't directly connected to one of the leading companies in the world, or isn't in an institution where there are experts in computational complexity or in representation? How do we create these for people who don't necessarily have those connections and those networks to top institutions? Jordi, maybe I'll let you go first.
That's another great question. One thing that I think is extremely important is that we're just very mindful of this and try to provide resources so that people can learn. You know, every time you write some, simple survey paper or something like this has a really positive impact, I think, on the world, because someone has a chance to understand a little bit more what you're doing. And also, for example, at Sydney, we've put a lot of effort into just doing basic machine learning courses for mathematicians who are interested in these kind of applications. So I think the education landscape is extremely important. Maybe I'll pass on to Moshe if he has other comments.
So if I look at my career, the interesting part, when I was at IBM, I was just what we call a pinhead theoretician. And I tried to do some kind of internal consulting at IBM, and it was not successful, long story. But then I went to ICE, and now I had an advantage that I didn't have to work with one company. I was able to work with any company. And I built a relationship with Intel that lasted almost 20 years. And what I learned from there is the gap between there is, I think, a cultural problem in computer science that some people train just as a theoretician, and that's what I need to do, just prove things. But proofs are hard, and all of us know that proving things are hard, and there are many problems that right now we just can't prove. And we can solve them fully analytically. And what I learned from Intel is you can take problems that are in theory computationally intractable, and you can build tools, and they work fairly well on real life problems. And this is a very vague concept, real life problem. Okay, but for Intel, it's not vague; it's the problem they need to solve, and the tools solve the problem. And now we need to figure out why. But I have become, actually my undergraduate degree was in physics. In physics, you understand that you need continuous interaction between theory and experiment. That theory would propose experiment, and experiment would shed light on the theory. We don't quite have the same healthy interchange between theory and experiment in computer science. But partly I learned it by seeing that, the people in industry often care about, okay, does the tool work? Does this idea work? Can solvers solve our problems? And that was being the fact that there is industrial demand for this. This has been a huge, one reason that this tool have advanced so much, because people are willing to invest the time to develop better tools, because there are people in the industry says, we will use whatever you give us. Bring it on. As opposed to, people in academia just talking to themselves. So, innovation requires a healthy ecosystem where you have the pinhead theoretician, but idea pass all the way from the theoreticians all the way to people who build industrial tools. And the healthier the exchange between the different layers in this ecosystem, the healthier the ecosystem will be.
So I think we're coming to the end of the time. And so the organizers can stop me if they should, but I have one last, hopefully brief question for both of you. And so what advice would you have to someone 21 finishing college and thinking about entering into a life of doing research and scholarship? How should a young person navigate the world that we find ourselves in now? What should they learn? How should they approach research? What are the tools that they need in order to do interesting things going forward? Maybe Moshe, you can go first.
So when I talk to prospective undergraduate students think about doing a PhD, I tell them that you don't make PhD for the money. You go to do a PhD because you get bored very easily. And you want a job where you will never be bored. And then I tell them about my life when I was in the military, in the IDF. and I went to parachuting school. And I had the experience of being the first in line to jump, which means for about 1 minute, standing in the open door of a jet plane, going in a speed of about 500 kilometers per hour. And you're leaning outside, you're holding though, you're leaning outside. And this is, there's no moment in my life I've been more alive as you are standing, leaning outside of an airplane. I tell them, this is what research is like. You're holding for your life there, but you're sticking your head into the unknown. And this being at the interface between the known and the unknown is intellectually just incredibly thrilling. There are people to whom this sounds exciting. There are people to whom this sounds scary. The people to whom this sounds exciting, they may end up doing a PhD.
Jordi?
Yeah, to add to that, I think it's very important to realize that it's possible to really take one's time to try to understand something. So I think that the history of deep learning is very interesting in that there was, 30 or 40 years where it was not a very fashionable, neural nets were not very fashionable. I remember looking at it in the mid 2000s thinking this is not a particularly good idea. But there were some people that were convinced that it was a very interesting thing and kept going. And at various points during my research career, I've had a sense that something is extremely interesting and it's not something that everybody's interested in. And I think it's very, very important to follow that urge and to stay true to your mathematical soul, wherever that is, or your computer science soul.
If I may interject, I think Jan LeCun should be on the call. But when Bengio, Hinton, and LeCun received the Turing Award, I think it was just a few years ago, 2018, I think, if I remember correctly, the citation explicitly referred to their tenacity, to the stuck to this idea that everybody's given up, or neural net don't work, and they stuck, and they stuck to their guns, and they kept working on it, and eventually, of course, it became a huge success. So their tenacity was so unusual that it was explicitly remarked on in the award citation.
Well, I think that is a perfect segue for me because, in fact, Jan LeCun is our next moderator. And in 2 minutes, it is that we need to hand off the baton. So thank you, Jordi. Thank you, Moshe, for fascinating comments. And thank you for the National Academies for creating this forum. And let me hand the baton to Jan LeCun. Thank you all.
Well, thank you for this wonderful session. Okay, I'm Jan LeCun, or Jan LeCun, and a pleasure to introduce the speakers that we have in this session. The first speaker is François Charton, not from Facebook AI Research, from Meta, and FAIR now means fundamental AI research. And François's work has been fairly fundamental in using deep learning for mathematics. You have the floor, François.
Yeah, hi. Yeah, I'm going to try to share my screen. Can you see my screen or not?
Yep.
Yeah, and now you can see it full, hopefully. Is it the full screen? Oh, yeah.
Yep, works.
Okay, so hi, I'm François Charton. Yes, I work in Meta AI, and I'm going to talk about reasoning with transformer. And to start, I'd like to confront you to a cherry-picked exchange between me and a very famous LLM that you'll all recognize. What's interesting, okay, it's a question, you can prove that ChatGPT cannot count, and it doesn't count well. What's interesting is that even if ChatGPT here had replied correctly to the question, the whole problem is that the reasoning is wrong. So you can have the question right or wrong. The problem is that the explanation it gives of the reasoning shows that obviously something is very wrong in the way it processed the question. So more generally, I'm interested in trying to solve problems of mathematics with transformer. And the way I look at the problem is that I want to think of mathematical problem solving as a translation task. So I want to train transformers on generated sets of problems and solutions to translate a problem, which can be represented as a mathematical sentence or statement, into a solution, which is another mathematical statement. So for instance, confronted with an input of a sentence that would be 7 plus 9, 3 words, I would like the transformer to translate 7 plus 9 as 16, which could be 1 word, 16, or maybe 2 word, 1, 6, if you prefer, up to you. Or if I'm given, a polynomial as a sentence, x squared minus x minus 1, I just said it, I would like the transformer to be able to translate this into a pair of roots, which are the roots of the polynomials, or something, important about this polynomial. So that's the way I'm looking at problem solving and math with transformers. So to give you a more precise example, suppose I want to learn the greatest common divisors of 2 integers, say 10 and 32, the GCD is 2. I can encode those numbers, the input, as sequences of base 10 digits, the way you write them. It's a perfectly legitimate sentence. So that would be +1 0, +3 2, and the output would be +2. And I want my transformer to just learn to translate the first sentence into the second by just seeing many examples and as a pure language problem. The model will never know any math in this process. In fact, I could replace all the mathematical symbols by words of any choice. It could be dog, plum, banana, dog, something, something. I could replace all the names by words or by anything, images, whatever. The transformer would not care. It would still work. So the magic of it is that this works. It might seem strange, but using this approach, we could, over the recent years, compute the symbolic integral of a function and do it as well as Mathematica, MATLAB Maple. So that was with Guillaume Lampe in 2019. We could discover properties of differential system. Is a differential system stable around a point? Is it controllable? That was with Amaury Ayat. I could work on translating a matrix into its eigenvalues or a polynomial into its roots. We could last year with Stéphane Dascoli discover integer recurrence, basically predict the next number in a sequence like you do in IQ test. And you can even do things that are moderately useful and anyway hard, such as attack crypto systems. I do cryptography as in the Turing presentation in the beginning. So we showed with Cathy Lee that you can attack learning with error, which is one of the main public key crypto system, which is considered by the National Institute of Standards in the US for post-quantum cryptography standardization. So you can go a long way with this. The problem is that every time you solve a problem, there's a question. The question is, has the model learned to reason? Has the model learned the underlying mathematics? And I want to show that, well, it sometimes happens, but it's not always the case. And this raises a number of interesting questions. So I'm back with my GCDs. I'm back with rational arithmetic with transformers. That's my first example. And the idea is that, okay, suppose I want to compute fractions, compute with fractions. So if I give a transformers 4 integers, A, B, C, D, I can very easily train it to predict whether 2 fractions, how to compare 2 fractions, whether A on B is larger or smaller than C on D. By easily, I say I can train a very small transformer with less than 100,000 examples, which is very little if you think that it starts from scratch, and achieve 100% accuracy on any fraction, seen or not seen at training. But funnily enough, if you try to do the same thing but compute, the sum of the fraction or the product of the fraction, it never works, or at least I could never make it work, even having huge transformer like 1 billion parameter, which is unrealistic given the small problem I have, or no matter the amount of data I throw at it. Actually, I couldn't even simplify A on B. If I gave 2 integers and I want it to get a fraction in simplest term, it doesn't work. So this brings a question, could you learn the greatest common divisor? So you see the method is always the same. I'm going to generate pairs of integer, in this case, random pairs of integers between 1 and 1 million, uniformly sampled. I'm going to compute the GCD with any favorite tool you might have, Python or whatever, and train a transformer on it. And see, every once in a while, I'm going to test it on a HAL data set, 100,000 examples, not seen at training, and see how it works. And the funny thing is that, again, it works, and it works pretty well. So I'm using here, I'm encoding my input and output numbers in base 30. So why 30, we might wonder? Well, the idea in the beginning is that you want a large base so that the sequence do not grow too long. It helps the machine. And I had that hunch that possibly composite base might work better. It's just a hunch. There's no very good reason for that. I used the smallest transformer you can imagine. There's only one layer, 64 dimension. You couldn't do language with that. It's less than 1 million parameters. It's ridiculous. But on 2 experiments, after just one epoch, 300,000 examples, I achieved 85% accuracy, which means 85% of my test set problems, which were GCDs, randomly sampled, but not seen at training, were correctly solved by the model. And if I train for longer, I end up at almost 95% accuracy. So, you know, when you see that and you're an AI scientist, that feeling that this is your hype moment, spotlight, and you're going to claim that you've solved an important problem of arithmetic and all that, and all that, surely you have learned the math. Well, until you look at the same experiment when you encode the input and output in base 31, not 30, 31, and then you get the green curve. And accuracy is at 61% and plateaus there. And this sounds wrong, right? And if you try more bases, you get those nice stacked curves. So from top to bottom, you've got base 30, base 6, base 10, base 2, base 3, base 31. And yeah, it doesn't work. The GCD should not be base dependent. It should not be dependent on the representation. It's the property of the integers. So what's happening? So in order to understand that, I can leverage the math I know about GCD, and I can look at my model prediction. So the first thing about the math is that we know that the probability of the GCD to be k for 2 random numbers is proportional to 1 on the square of k. That's an old theorem by Cesaro. And if you look at the model predictions, so it means that 61% of random pairs have GCD1. You remember we've seen 61% as the base number we got, that's this one. And if you look at model prediction and failure case, you can notice that 1, the likeliest output, is predicted by default, giving it, you know, a baseline of 61% accuracy. But there's more to it. The model apparently only learns the GCDs that are products of the prime factor of the base. So for instance, for base 2 or any prime base, there are other tricks for composite base. In base 2, GCD 1, 2, 4, 8, 16, all the powers of 2 are learned to perfection, to 100%. And all the other GCDs are wrong. But they're not randomly wrong. They're not hallucinatively wrong. They're very principled wrong. Basically, you can, if you look at them, you can notice that the model actually does something. It counts the rightmost zeros in binary representation. So suppose you want to calculate the GCD between 28 and 14. 28 in base 2 is 11100, so 2 rightmost zeros. 14 is 1110, 1 rightmost zero. The machine decides that, okay, there's 1 common 0, so GCD is 2, and predicts 2, and it's wrong. Note that sometimes it's right for 60 and 56, it works. It predicts 4, which is the right GCD. So sometimes it works, but, you know, looking at that, you can understand what happens. You know, in base 30, you get right GCD 1, 2, 3, 4, 5, 6, not 7, 8, 9, 10, not 11, 12, not 13, etc. They're all correctly predicted, hence the 95% accuracy. And in base 31, you only get to predict correctly 1 and 31, hence the 61% accuracy. So the bottom line is the model is cheating, clearly. It's exploiting representation to compute the easy case and failing on all of this. And this is important because, you know, very often when you evaluate models and reasoning, you just have a test bench and you say, okay, look, I got 60%, 70%, I broke SOTA on this, etc. I got this result. What's important here is that you can get excellent results on the test sets, yet do very unlikely things and not have learned to reason. At this point, some of you might wonder, you know, is it worth learning math with transformer? Because if you cannot compute a greatest common divisor. So I'm happy to say that it's still possible to learn the greatest common divisor. And for that, there is a trick. This is ongoing research, so this is not finished at all. You remember when I built my training sample, I selected all my numbers randomly between 1 and 1 million and uniformly. The thing is that it means that the model is mostly trained on large numbers, number over 100,000. 90% of them, of those numbers are over 100,000. But that's not how we train students or children. You know, we train them with short examples first and more short example, large examples, so that they can generalize. So why not try the same? So I sample my data logarithmically, Benford-like, so that I have as many one-digit number as two-digit number up to six-digit numbers. So the larger the number, the less often it appears. I use a slightly larger model, and you can see the training curve over there. You can notice that we're still not at 100%, so the GCD is not quite learned, but the problem with different base have totally disappeared. So the shortcuts that were learned there can be eliminated, and some form of reasoning or better form of reasoning maybe can be learned if you manipulate the training data distribution. And this is important because this is something we never do in language, but it makes a lot of sense in math. So having shown that sometimes you don't learn the math, I would like to show now an example where the math are learned, the underlying math are learned. So this time, it's also calculation. I'm starting with a symmetric matrix. So symmetric matrix is basically an array of digits. So it can be represented as a sequence of numbers, and the numbers can be represented, as we've seen, as sequences, so sequence of sequence. And given this symmetric matrix, I would like to predict a vector and a matrix such that, you know, HM H transpose equals HM H inverse equals the diagonal with D. And so I want to predict, you know, find a vector D and matrix H verifying that, providing the models only with triplets, with examples, pre-calculated examples. So that's the problem the model is going to solve. But we have theory, and we know from theory, this is the spectral theorem, that the Ds are basically unique because they're the eigenvalues, they're unique up to a permutation, sort them and they're unique. And H is unitary, in this case orthogonal, and its rows and columns are all 2 by 2 orthogonal and all have unit norms. So the question I have is that, okay, suppose my model learns to calculate, you know, to predict D and H from M. Is it going to learn the theory? And what does learning theory mean, actually? So for that, what I'm doing is that I'm training a model. I managed to train it to 92% accuracy. And having done that, I'm going to test it on a very large sample of matrices, not seen at training as usual, 100,000 matrices. So I'll get 92,000 correct prediction and 8,000 errors. But what I notice is that in all the test case by 6, so that's almost really all test case, the correct prediction and the wrong prediction, the eigenvalues are correctly predicted with less than 1% error. And in 99% of the test cases, so the correct, but also most of the errors, all the rows and columns of H have unit norm, which means, and I'm stating that those two properties have been learned because they're respected. This invariance is respected even when the model fails. So in this case, I say that, okay, the model really seems to be learning mathematics. And it goes further because if instead of training my model to 92%, I sort of stop training early, you know, I half train my model to 70% accuracy. Still, the eigenvalues are correct in 99.6% of the test cases. And the rows of columns are pretty much always have unit norms. So you see, these results, it's not a cherry on the cake when, you know, when the model learns to compute and then at the end it learns the theory or the properties. The properties seem to be learned early in training. Another interesting experiment, if you go for a harder case, the matrix I had here was 5 by 5. If I get 6 by 6 matrices, my model is too small. That's not enough capacity to solve the problem. So it's going to achieve about a little less than 50%, 43% accuracy. Yet eigenvalues are correct and rows of columns have unit norms. So again, those properties, those mathematical properties seem to be very resilient, which I think proves that to some extent, or in some ways, the transformer are actually learning the underlying mathematics. And this brings a lot of, you know, ideas, because if you look at this specific case, there were lots of ways the model could fail to predict, but we have sort of narrowed all the failure case, all the 8,000 failure case in 100,000 examples to just a single cause, which is that due to the rows and columns of H not being quite orthogonal. They're mostly orthogonal, but not quite. So it's not the norms, it's not the eigenvalue, it's really the eigenvectors that are not, you know, matrix is not quite orthogonal. And it's interesting because it shows that, you know, whereas in language, people speak of hallucination or confabulation, you know, the case where you ask a question and the model is lost and say something totally irrelevant. Nothing is irrelevant here. All the predictions are roughly right. You know, they make sense. They're bad approximation of the correct solution, but they still are approximations. I think this is mostly due to the fact that we supervise the training, but it's an important thing because it's not, what is usually said about language models. So I'd like to finish on something. You saw that previously for the GCD, the greatest common divisor, training data sort of saved the day, managed to do things. So can we do the same? Can we pull the same stints here? So I'm looking at a simpler problem where instead of computing eigenvalues, eigenvectors of a matrix, I'm only computing the eigenvalues. So it's an easier problem. And for this, if I have independent, identically distributed coefficient, my model will predict eigenvalues with 100% accuracy for any matrix between 5 by 5 and 8 by 8. But what am I exactly doing here? The thing is that I'm learning to calculate eigenvalues, but the matrices I have are called Wigner matrices, and they have a special distribution of their eigenvalues because the coefficients are independently identically distributed. Their eigenvalues are distributed according to a semicircle law. So what problem exactly have I been solving? Am I solving diagonalized eigenvalues or just eigenvalues of Wigner matrices? So if you try to test the model so that the columns on ensembles of matrices, test sets with different distribution of the eigenvalues, like uniform, Gaussian, Laplace, or sets of matrices which are only definite positive, matrices are not definite positive, then you can notice that if you train on Wigner and test on Wigner, it's perfect. But as soon as you change the distribution you want to test on, the wheels start to go off. So uniform, Gaussian, Laplace, it doesn't work, 35%. And for positive matrices, it doesn't work at all. So it looks like we're only solving the eigenvalues of Wigner matrices, which is impressive already, but it's not, as nice as we'd like. The funny thing is that if you train, you can again manipulate the training data distribution. So here, the lines in the table represent the training set I use. So the first line is the one we've seen, I trained on Wigner. The bottom lines, I trained only on positive definite matrices. And if you train on positive definite matrices, you're going to predict the eigenvalues of positive definite matrices, but not the others, because basically the model has never seen a negative eigenvalue. But the funny thing is that if you train on strange ensembles, matrices, symmetric matrices with Gaussian or Laplace distributed eigenvalues. So those matrices are weird, their coefficients are not independent, or they would be Wigner. So they're not the kind of the first ensemble of matrices you would think of as training sets. But the point is that if you train on them, you get 100% on those matrices, but you also get to generalize to all Wigner matrices and even to positive definite matrices, even though none of those matrices are positive. So you can generalize way out of distribution because of this. So again, what I'm saying here is that once again, the data distribution matters. Training data distribution matters a lot, and you can achieve a lot of things with that. So I'm almost done. Yeah, a fun fact is that those distributions are good because not only do they generalize, but they also, models trained on the distribution also learn faster and scale to larger dimensions. So they seem to be very sort of magical. So I'm sort of finished. So the main takeaways is that test sets are not sufficient if you want to understand whether the math are learned. We've seen that with the GCD. You can have very good results on the test sets and catastrophic results, when you look at what is actually learned. You need either interpretable model, but right now transformers are not really interpretable, or you need to work on the failure case analysis, which means that you need to work on problem when your model fails. But then transformers do learn the underlying arithmetic. This works. And finally, which is something that doesn't happen in language, but happens here, training distribution matter a lot. There's a lot you can achieve with training distribution. So yeah, that's the end of my talk. And I leave you with this strange exchange with ChatGPT, which gets, well, the reasoning sort of right, but all the details wrong. Thank you very much.
Thank you, François. Just going to ask you a very quick question, which disappeared from my screen just now, from Talia Ringer, who is one of the co-organizers of this meeting. Is there a predictable relationship you have observed between the number of layers and the ability of the transformer models to learn those functions? Is there limits? Are there limits to just stacking more layers?
So most of the examples I have here are with very shallow transformers. The GCD is only one layer. You can go lower. What I've noticed is that if you have deeper transformer, usually you will be able to scale to longer sequence and learn faster on larger problem and longer sequence. But the depth doesn't seem to be as correlated to the performance as people, in language tend to think. For instance, for the cryptographic problem, we are using extremely shallow models. We're using shared layers, which make them even shallower, but using extremely shallow model. And every time we try to go to deeper model to improve, it doesn't. So there's sort of a mystery here, which might be due to the fact that the transformer architecture was created for language, which has a number of specificity. And when you want to apply it to different, objects like scientific objects like math and physics and all that, maybe some of the architecture thing that have been invented, sort of hamper the thing. I'm thinking of all the normalization things and the skip layers and all that.
Okay, so by shared layer, you mean you're reusing the same parameters at every stage.
Exactly,
right?
that's a loop in the layer.
Repeating the same operation multiple times.
Exactly, you have a loop in the layer and you loop, and usually you have a loop and a gate inside the shared layer. So the gate is just there to say, do we iterate or not? So every time you see a token, because you have tokens that you can do in one loop and tokens that need 6 loops. So typically you have that combination of a gate plus a loop, and you have 1 or 2 or 3 layers, but the layers are shared. Yeah.
I see. Okay. Thank you. We'll keep the remaining questions for the general discussion. Our next speaker is Adam Wagner. He's an assistant professor of mathematics at Worcester Polytechnic Institute, and also a consultant at Google, DeepMind. And he's going to tell us about funny counterexamples via reinforcement learning.
Yeah, thank you so much, Jan. I think you can see my screen well.
Yeah, we can see it.
Perfect. Yeah, so thank you again so much for the opportunity to talk on this absolutely fantastic workshop. And the main idea of my talk will be the following. We have all these companies, such as Google DeepMind, for example, that have created all these programs that can play chess, Go, Atari games at superhuman levels. And the real interesting thing about these programs is that they started from knowing only the rules of these games, and they figured out everything else just by playing the games many, many times, just by themselves. So given the success of all these self-learning algorithms, these so-called reinforcement learning algorithms, how nice would it be if we could find a way to use them in mathematics as well? So you can imagine that instead of inputting the rules of chess, you could go ahead and input the rules of a one-player game where the goal of the player is to construct a graph with as many edges as possible without any cycles of length 4. You can kind of imagine how something like this could be phrased as a game. You have a player, you start offering each possible edge of an n-vertex complete graph to the player one by one. For each edge, the player can decide, do I want this edge in my final construction, or would I like to reject this edge? After we have offered each possible edge to the player, they end up with some kind of final graph. At this point, the game ends, and we have to give some kind of feedback or score to the player that represents how well they did in this game. And in this particular game, the score could be something like you get 1 point for each edge that you included, and you get, let's say, a 100-point penalty for every cycle of length 4 in your final construction. So that's the idea. We take a mathematical problem, we phrase it as a game. Now we throw the reinforcement learning algorithm at it, tell it, try to get good at this game. Then we go away on a holiday for a week, and hopefully when we come back, we found a program that's very good at constructing graphs with many edges and few force cycles. So the reason this would be good is that if this approach works, then this would be an extremely general way to attack open conjectures in mathematics. You can just take any open conjecture that could potentially have a finite counterexample. You could phrase it as a game, and then you could tell the reinforcement learning algorithm to try to get good at the game of finding a counterexample to this conjecture. So that's the idea. We will see how well this actually works in practice and whether we can do something interesting with this approach. That's a very quick disclaimer. I am a mathematician, and I've only been getting into machine learning the past couple of years. So please take everything I'm saying about machine learning with a big grain of salt. All right, so let's begin. So let's talk about what we actually hope to achieve in this talk here today. I already told you that our goal is going to be to find counterexamples to conjectures by using some reinforcement learning. But this is very, very vague, so let's be more specific about what we actually hope to achieve. And first and foremost, here in this talk, we are going to try to avoid giving the reinforcement learning algorithms any help at all. So, of course, this is not a practical decision. In practice, you would never try to solve a problem in this way, but I'm curious how well this approach can work, how well these reinforcement learning algorithms can work if I don't help them with any human insights at all. Now, once you make this first assumption and you accept this, it will have some consequences. Namely, it will mean that I cannot change my setup between different problems, and I cannot change the hyperparameters. I will have to be forced to create one simple baseline algorithm, some very, very simple learning setup that I can just throw at 100 open conjectures and hope for the best. So that's what we're going to try to do here today. And let's see what happens if we actually do this in practice. Let's start with a baby example. Here is a conjecture from the literature that says, so this conjecture is false. We know it has some counterexamples. And this conjecture says that for every graph, the sum of its largest eigenvalue and its matching number is always at least some function of the number of vertices. So I would like to ask all of you to try to forget everything you know about graphs. Let's completely ignore what eigenvalues and matching numbers are. And let's ignore where this conjecture comes from and what the motivation for this conjecture is. Let's focus only on how we would go about disproving this conjecture if we didn't know any mathematics at all and we wanted to use only reinforcement learning. Well, in its simplest possible form, we need to do two things. We need to first decide how should we phrase this conjecture as a game, and then we have to decide what the reward function for this game should be. Phrasing it as a game can be done in multiple ways. One of the simplest possible things to do is what we did on the first slide. We pick the edges in an autoregressive way, so edges one by one, and we make a decision on the next edge based on all the decisions we've made so far. That's a very simple way to do that. Let's go with that here. What should the reward function be? Well, given that we've constructed a graph, the reward function should signal how close this graph is to being a counterexample. Here, we want lambda 1 plus mu to be small, so an obvious choice would be lambda 1 plus mu. In this case, we want to minimize it, but that's the same as maximizing minus lambda minus mu. In its simplest possible form, that's all you need to do to get started with reinforcement learning. You define the game, you define the reward function. Now you can throw the reinforcement learning algorithm at it. And if you do that and you come back a week later, this is what you will find. So here, the blue line represents the best score that the program was able to achieve after as time progresses. You can see in the very beginning, it had absolutely no idea what it was doing. It was just generating random graphs. Then it very quickly decreased. And eventually, over time, the score function dropped below this orange dotted line. Now, this orange dotted line represents the right-hand side of this inequality. So the fact that eventually blue line dropped below orange simply means that at this point, the program was able to consistently find counterexamples to the conjecture. And that's often all there is to this method. Once this happens, you can look at what the counterexample is that it found. And this is actually one of the smallest counterexamples to the conjecture. Weirdly enough, it seems to be true up to n equals 17. Another thing you can do is you can see you can look at how the best constructions have evolved over time. In the beginning, it was just generating random nonsense. Very quickly realized that the sparse graphs are the way to go. And eventually, this kind of balanced double star structure has emerged. Okay, so this was a baby example, and it was kind of a dream scenario. Everything worked exactly as we hoped. There was an obvious choice how we phrase it as a game. There's an obvious choice for reward function. We plugged it into the reinforcement learning, and it worked. If this happens, there's nothing much to say. But I can tell you from experience that in the overwhelming majority of the cases, if you try this approach, it's just not going to work at all. What I want to do here in this talk is I want to show you 5 more examples what could happen in practice. And I picked these 5 examples in such a way that each of them will illustrate some different aspect of what could happen when you apply this method in practice. And the goal is that by showing you these examples, you will have a good idea what it looks like to actually apply these methods, perhaps even to your own problems. So let's get started with these examples. The second example I want to show you is going to be very, very similar to the previous baby example that we looked at. But that's for a very good reason. So this is a conjecture from 2016. It's open, and it says, similar to the previous one, that for every graph, the sum of two parameters, the proximity and some distance eigenvalue, is always positive. Let's again completely ignore where this conjecture comes from and what these two functions, proximity and distance eigenvalues, are. Let's focus only on the reinforcement learning aspect of it. Once again, we need to do two things. We need to phrase it as a game. We can do it in the exact same way as before. And we need to decide what the reward function should be. Well, previously, the reward function was lambda 1 plus delta, lambda 1 plus mu. Now, the only thing we need to change is change lambda 1 plus mu to pi plus delta. Otherwise, we might as well use the exact same program as we did before. We plug it in for n equals 30. We go on a holiday, and when we come back, this is the graph that we find. So this is the best graph the program was able to produce for this particular problem. Value of the reward, pi plus delta for this graph is something like 0.4. But if you look at the conjecture says that pi plus delta is always positive. So the fact that pi plus delta is equal to 0.4 here means that this graph, which is the best graph the program was able to find, is not actually a counterexample to the conjecture. So this is an example where reinforcement learning was not able to find a counterexample by itself. And this is a very, very common thing that happens. But often that's not the end of the world, because often just by looking at the best construction the program was able to find, we can get enough insight to then step in and finish the job ourselves. So in this case, if you take this graph, you put it on a tray, you take it to any undergraduate mathematician, it will be completely obvious to them what kind of graphs they should be playing around with if they hope to find a counterexample to the conjecture, because you just take this flower, increase the number of petals, start playing around with the lengths of these two branches. And it turns out if you start playing around with these things like this, there's no way that you will not eventually find a counterexample, because already something like this happens to be a counterexample to the conjecture. So this was an example where reinforcement learning by itself did not manage to refute the conjecture, but it gave us enough insight so that a human could easily step in and finish the job from there. The next example is going to be just to show that this approach has absolutely nothing to do with graphs. Any problem that can be phrased as a finite sequence of finite decisions can be attacked in the exact same way. So let's have a look at this question here, which asks, how large can the permanent of a 0-1 matrix be if it doesn't contain a 3-1-2 pattern of ones? So the pattern that's forbidden is 3 ones in this particular configuration. So dark squares denote ones, white squares denote zeros. So in particular, you're not allowed to have 3 black squares in this kind of configuration. The question is, how large can the permanent of such a matrix be? Okay, so well, first of all, in terms of how to rephrase it as a game, we might as well do the same thing as we did before. Previously, we offered edges 1 by 1. Now we can go over the entries of the matrix 1 by 1, and for each entry, we can make a 0 or 1 decision. So that's very similar to what we did before. But more difficult question is, what should the reward function for this be? And now there are a couple options that you could consider. If you want to take into account that the permanent should be large, but also that you shouldn't contain any of these forbidden patterns, one option that you can do, and that's not the only possible thing you can do, is have the reward function be the permanent of the resulting matrix minus some kind of function, penalty function, depending on the number of the forbidden configurations in the final construction. So this works, but you do need to be careful that the penalty function is big enough, because otherwise your model might learn that it's beneficial to include some of these forbidden copies because the gain in the permanent outweighs the loss you get through the penalty function, and you end up solving a completely different problem, which is not something you want. But as long as you don't make this mistake, this works pretty well. And you end up finding some pretty good constructions, and this also refutes some conjecture that was in this area. And one more interesting thing to me was this really bizarre thing that if you look at the initial segment of these numbers, you see these powers of 2's that for some really strange reason seems to break down at n equals 8, where the answer is 120. I have absolutely no explanation to why this is happening. Okay, so far we've seen a couple of examples where it is always obvious how to phrase these problems as games. As we move to more complicated conjectures, that is not always the case. Let me show you one example where it's not quite obvious how to phrase this as a finite sequence of finite decisions. Here's a conjecture. Let's not worry too much about what the conjecture actually says. Important thing is that it says something about trees. It says that if you have a tree, then two coefficients of some polynomials are close to each other. Now, how do we phrase it as a game? You could say, let's do the same thing as before. Let's generate a graph. And if you do that, then the reward function would have two components. The first one would measure how close this graph is to being a tree. And the second is how close these two coefficients are to each other. This would work in theory, but in practice, you can do much better than that. Usually, if you have a reward function that consists of multiple components, if there's a way to remove one of the components, that will help the learning a lot. So let's think, is there a way we can remove one of these two components from the reward function? Well, F2 is the conjecture itself. You're not going to remove that. Is there a way to remove F1? Well, that would mean that we need to generate trees directly. That would mean we need to find a bijection between trees and some finite sequences of finite decisions. Is there a way to do that? Yes, there are many ways to do that. One of them would be, instead of generating a graph, we could generate its proofer code, which is a bijection between trees and words of length n minus 2 from an alphabet of size n. If you do that, instead of generating graphs, this gets rid of this first component, and you're left with F2. Learning will be much faster, and you end up finding a counterexample. Unfortunately, this is not always possible. If we start working with more complicated conjectures, many times, I don't know how to do this. And usually when this happens, this is a signal that the reinforcement learning approach is just not going to work very well. So here's a question. Do there exist two graphs so that they have the same distant Laplacian spectrum, whatever that means? One of them has some kind of weird property, and the other one does not have this weird property. Okay, imagine we have constructed two graphs. How do we evaluate how close this pair of graphs is to being an answer to this question? Well, it could be something like this. We could have a score function consisting of three components. First one measuring how close their distance Laplacian spectrums are to each other. The second one could measure how close G is to having this weird transmission regularity property. And the third one could measure how close H is to not having this property, maybe a penalty function if it has this property. That would be a straightforward way to do it, but then you have a score function that consists of three components that are all learning some very, very different things. In practice, my experience is that if this is your score function, then you can throw reinforcement learning out the window. It's just not going to work at all. And in this case, there's no obvious way to remove any of these three components. If this happens, your best hope is that there exists some small enough counterexamples that you can still find it just by brute force, which in this case happens to be the case. But usually, this usually means to me that other methods are much better suited for this problem. All right, let's look at one last example. So far, all the examples were about finite graphs. But of course, the most interesting conjectures in mathematics are about what happens when n goes to infinity, what happens in the limits. Is there a way to attack these problems using reinforcement learning? Well, it's definitely much, much harder, but occasionally there are ways to do that. There are some tricks that you can use. So let me show you just one example of this. This is a conjecture from Erdős from 1962. His conjecture says, take a graph, count the number of 4 tuples of vertices so that all two of them are connected to each other by an edge. Count the number of 4 tuples of vertices that no two of them are connected to each other by an edge. Add up these two numbers. He conjectured that this sum is minimized by random graphs where you flip a coin for each edge and you include each edge. If you flip heads, and you don't include Euclid tails. But of course, this conjecture only makes sense as n goes to infinity. So any counterexample to this conjecture has to be an infinite sequence of graphs. So this was a famous conjecture. It was open for 27 years until a breakthrough result by Andrew Thomason showed that this is false. And we, together with Grange Ray, who is an absolutely brilliant computer science professor in Belgium, tried to refute this conjecture using reinforcement learning. And we found a way to do that, but it uses some tricks. And we used a standard trick in graph theory, which is instead of constructing an infinite sequence of graphs, we only constructed one finite graph G, and we just took the direct product of this graph with a complete graph of m vertices, and we just let m go to infinity. This is a very standard trick to reduce infinite conjectures in graph theory to finite conjectures. And once you have this, you can just use this complicated looking, but actually very simple limit object as your reward function. Once you have this, everything else is the same as in the previous examples. You plug it in for the right value of n, and if you're lucky, you end up finding a counterexample. To me, there are two takeaways from this last example that I just showed you. First one is it shows me the power of this method, namely that if Erdős had made this conjecture today, then it definitely wouldn't have been open for 27 years. We would have found a counterexample either with this method or with some other computer methods, for sure, very quickly. But it also shows me a big drawback of this method, namely, if we look at the actual counterexample we found, it's just some graph like this. I have no idea what this graph is, and I get absolutely zero understanding from looking at this graph. The only one bit of information I really get is that the conjecture is false. But if we look at the paper of Thomason, there's no doubt in my head that reading that paper, you get much, much more understanding than by just looking at a computer-generated counterexample. This tends to be the case for such complicated conjecture, and it's an important drawback to keep in mind. We get much more understanding through some human proofs. I'm going to stop here. Thank you very much for listening.
Thank you very much, Adam. Okay, we have a series of questions. I'm actually going to start with a question for you, Adam. So you're talking about reinforcement learning. Now you haven't talked very much about the kind of method you've been using for those problems. But I'd like to ask you to what extent those are specifically reinforcement learning method or just merely gradient-free optimization. Like, you know, let's find a combination of a configuration of input variables that will, you know, optimize a value function. Given that generally in reinforcement learning, there is kind of the sequential aspect, right?
Yeah, absolutely. So I didn't talk about the reinforcement learning setup at all. So I used an autoregressive setup. I predicted the next edge based on all the previous decisions I made. So in particular, this means that this method that I just presented will definitely not scale very well. And it has a bunch of other issues as well. So it's definitely a very, very, very inefficient way to attacking these conjectures. But in these examples that I showed you, I tried to find the counterexamples with other ways, and I couldn't. That's not quite true. The first baby example, you can definitely find a counterexample many other ways. And in the very last example, other people and also we managed to reproduce it without using any reinforcement learning. But in the other ones, I didn't. And as far as I know, nobody else has managed to reproduce these counterexamples without using some kind of learning.
Okay, so basically, you for some of those things, you're turning it into kind of a sequential decision process. And are you learning a policy?
That's exactly right. I picked the simplest possible policy-based method I could find. Just use the cross-entropy methods, and as you said, just sequentially generates all the decisions. It was funny because when I started out, my first instinct, and I had no idea what I was doing, my first instinct was just, I'm going to throw AlphaZero at all of these problems, and it's going to work beautifully. And I remember I had like half an hour until lunch, and I thought I could easily finish it in half an hour, and it will be beautiful. And of course, 2 months later, I gave up. But even then, I didn't realize what I was doing wrong. And even after that, I went for some very, very complicated setup. I don't remember, some variant of DQNs that I found in some very recent paper, and I coded it up. And the worst experience of that was that it took me a long time to code up. And eventually it didn't crash anymore, and it was learning. But it was only through a lot of pain that I later understood that just because a neural network is running and not crashing, that doesn't mean that I didn't make 100 mistakes by coding these things up. So that was a big lesson to me, that learning that all these neural networks can actually fail in a very silent way. That it seems like it's learning, but
it's something that Francois also sort of pointed out, right? It seems to work, but it doesn't actually work. Actually, a related question asked by Andrew Sutherland on the forum. It's really the same question. Have you tried to quantify the performance of reinforcement learning relative to local search algorithms like hill climbing of various types, simulated annealing, or other types of gradient-free algorithm?
Yeah, that's a good question. I don't really know how to do that. It's kind of a yes or no thing. Do you find a counterexample? Do you not find a counterexample? And we don't really have good baselines, and I didn't do good baselines. In these examples, the only difference I have is that I tried gradient-free approaches. They didn't work. Reinforcement learning did work. And I didn't test too much. I definitely didn't quantify how much RL actually helped in these cases. I suspect not much, just barely enough to take you over this edge.
Okay. Perhaps actually it's a good time to, for those of you who are listening and interested in those questions, there is a sort of community project, which is a large library for PyTorch of a gradient-free optimization method called Nevergrad, which has a whole collection of different things, that are kind of perhaps good to use as a baseline before looking for more sophisticated method in those cases. Okay, another question, which is for both of you, really. How do you think that combining sort of generic methods like LLM or transformers or things like that with sort of explicit tools that have hardwired mathematical abilities, like say Wolfram Alpha or something of that type, or a simulator, or a calculator or something like this? So this is something that generically, in the context of LLM, people called extended LLM or augmented LLMs. There's a lot of work in that area at the moment to basically give LLM some level of agency or some ability to plan. And so far the results have been mixed. But what do you think would be the usefulness of this in the context of mathematical reasoning? This is a question for both of you. Adam, maybe you want to start.
I'm not very familiar with how much it helps if you take an LLM and just throw some Wolfram Alpha on the top of it. It's definitely clear to me that LLMs are incredible things, but they're absolutely terrible at reasoning problems. And there's very good reasons for that, because like this method of predicting proofs just one token at a time just makes it more and more likely to get off course, and there's no way to recover anymore. So I feel like that itself is just not going to cut it. Maybe throwing some extra tools at the end, that's definitely going to help. But I feel like this real solution would be to figure out how we can make these, how we can change the architecture so that some learning and some planning can actually happen.
Right. What about you, Francois? You have a comment on this?
Yeah, my impression is that those approach, that they're put in the math and LLM thing, but they're a lot like code generation. So basically, instead of generating sentence, you ask the LLM to generate code, which are calls to API, which correspond to the Wolfram Alpha or whatever, whichever tool you want to use. So I think it sort of makes sense if it's about, finding a relatively small program with a small number of tools that are specific to the task. If the thing is about, calculating and choosing, suppose you're in a high dimensional space. And so it's not, you just want to take a derivative and calculate at zero. You want to select the partial derivative you want to do, and this several times, and then you'll compute something, etc. And you'll probably use a wide mixture of different tools at every single moment. I have the impression that if you do that, you reproduce exactly the one thing that is known to be difficult with LLM, which is the fact that, as soon as you want them to be very precisely doing a set of choice, and there's only one solution to every choice, like in reasoning, it doesn't work well. So another question is, how do you train such systems? Because, to train LLM, you need tons of data. Even if you manage to do it only at fine tuning, it's already a lot of data. Look at Minerva in the billion token to fine tune. It's not really fine tuning. So how do you train those models so that they work, on large enough examples for them to be useful? Because you cannot train them on one problem and expect them to generalize to different problems. It's always the same problem. So, so long you want to use them, if you want to add a calculator to do arithmetic in an LLM for word models, for word math problems and stuff like that, yeah, go for it, it will work. But if you want to do it for, harder mathematics or science or physics or stuff like that, where you have a lot of tools in complex series of experimentation, I have a lot of doubts about the approach.
Right. So there's been a growing number of papers from various people attempting to elucidate whether autoregressive LLMs of the, ChatGPT, GPT-4 style, whether those systems have a sort of implicit ability to plan. So in fact, they don't have an explicit ability to plan, right? Because they produce one token after the other using a finite number of computational steps, right? However many layers the transformer has to produce every token. So there's no real ability to sort of reason in terms of that would take a variable amount of time, right? So every token takes the exact same amount of time to produce, and it's not planned in advance. So one important question would be whether for mathematics we don't need some more explicit ability to plan, which is the case, obviously, like every AI system that has been produced to play complex games like chess and Go and diplomacy and poker, they have planning abilities. So they search through a tree or a graph of potential sequences of actions, which one will be likely to, minimize the cost or optimize the performance or whatever. And there's an explicit search mechanism. I'm aware that some of deep learning systems or machine learning systems that have been designed for mathematical proof also have planning abilities. I'm thinking of a project from some of your former collaborators, François Guillaume Lampe, who had produced a system that could solve something like 60% of the problems from the mathematics Olympiads, right? So those systems plan explicitly, but the current LLMs, the GPTs of the world, do not plan. So how do we combine for the purpose of mathematics? How do we combine the perhaps the fluency or the impressive emergent abilities of LLMs, autoregressive LLMs, with the planning abilities that people have developed in other contexts? It's a trick question.
So I think in proving, the thing is that they used MCTS basically. So we're sort of close to sorry.
Yeah, they do use. I mean, they use a version of MCTS, I think, in the.
So they use MCTS. So when you use MCTS, it works so long as you have a very good critic. So because you have a huge tree and you want to explore the tree, and you need to have a very good critic to know which nodes of the trees you want to explore. So again, everything is predicated at whether each step in the process, in the discovery or the planning, can sort of be. You can train a transformer or any other tool, but a neural net, you can train a neural net to predict next step or predict efficient next steps. Again, you're confronted with the problem of the data and how you train a tool to do that in a relatively general way. So I've seen it tried on symbolic regression, which is a purely mathematical task. You have numbers and you want to find a function, and MCTS works, but not impressively. Basically, it achieves state of the art, but it doesn't break everything. And I don't understand quite why, because it looks like a great idea, but it seems maybe it's just difficult to implement and difficult to engineer well. It seems very adapted to proving, in fact, because proving is really a grind. You have those steps.
Right. So for the benefit of the audience, MCTS means Monte Carlo tree search. So this is a technique. So, in classical AI systems for game playing, generally you construct a tree of, what are all my possible moves? What are the opponent all possible moves for each of the moves that I made? And you get this enormous tree of possible trajectories, essentially in the space of actions, which have to be discrete in that case. You can think of turning a mathematical proof or representing the set of possible mathematical proof in the same way. Every time you make a transformation in a formula or something like that, you generate a new branch in that tree, and for all the possible transformation you can make, you have a different branch. And as you increase the number of successive transformations, that tree grows exponentially. So what you need to do is have ways to either prune that tree, so you only explore the parts that are promising, or have a combination of pruning and random exploration, which is what MCTS does. So this has been incredibly successful in the context of games like Go. For chess, you don't really need it. You can do more explicit pruning without random exploration. But for Go, it's been crucial because the branching factor, the number of possible options at every time, is so huge that the tree is completely intractable. So in the context of mathematics, the branching factor is gigantic, if not infinite. And so you're faced with kind of similar issues there. You need some sort of oracle or trained system to tell you this is a good step. And this kind of connects with a question that people were asking previously about, or that I think we're going to talk about in the future, about the notion of intuition. Like, what tells you when you're in the middle of a proof whether a particular step is going to lead to a good result or not. In that sense, it's kind of very similar. Let's see. Okay, maybe some more specific questions related to your talks. Okay, here's a general question, actually, which is sort of perhaps a question of motivation for Francois. Someone for the audience asks, if we are to learn GCD via transformer, what does that change? We already have efficient algorithms to calculate GCD.
Yeah, I think the right way to ask the question is, if the transformer cannot calculate GCD, what does it mean? It means that, yeah, let's not use at least transformers and probably AI to do math or science and all that. The point is not, why GCD? Because it's a simple problem and because we have theory to interpret it. Do you want to use a transformer ever to calculate GCD or invert matrices or do eigenvalues? Of course you don't. Use NumPy, use all the tools you have. But the point is that if you can sort of show with a moderate, with a good level of certitude that it's impossible to learn this or that kind of problem, like, for instance, parity, it's understood that parity integration is an extremely hard problem, then it sort of helps define the use case where you can possibly apply AI or at least those in architecture or not. So, the point in that case is not to solve a problem that we can't solve with that. And it also provides intuition. For instance, the work we did on linear algebra we solve problems that NumPy solves much better than us and all that. But it provides the intuition that this kind of job was doable. And this is what sent us on, doing cryptography, which is in that case a hard task and something that we don't have to solve or attack. So there are two reasons. One, it provides intuition, and second, it helps define, what we want to find and where we don't want to go.
I guess a related question here asked by Kevin Buzzard on the forum. Are you really sure that you're learning the mathematics with Benford distribution?
Yeah.
Is what is actually happening that the machine sees all the small examples in the training data, so learns them, and then just guessing for the larger one? I guess that would be related to something that people in machine learning have been interested in, which is the question of curriculum learning, the fact that we start by learning concepts, as you mentioned in your talk, right? We start by learning concepts with kind of simple examples, and then we sort of generalize. But it's not clear this is a good approach when training machine learning systems.
Yeah, the original intuition for the Benford was an experiment with memorization. We tend to think that memorization is a bad thing. If the model memorizes example, then it doesn't learn and it's bad. But a lot of our easy math are done with memorization. Kids learn multiplication tables, and it's a good thing. So the idea here was to provide enough short examples so that the model might memorize the easy rules and then apply them somewhere else in some way. So as to whether it can explain the success, no. The thing is that so I've started looking at those data, but those are recent data. It doesn't explain the success because you end up learning things that you didn't learn before. For instance, a divisibility by 7 used to be something totally unlearnable in any base, except base 7, obviously. So in this case, I see divisibility by 7 appearing in my examples. In some of the examples, it seems also very delicate. From one initialization to the other, I get different result, different success, and the errors are not the same. So everything shows that I'm still missing a piece in understanding what happens. The only thing I'm saying is that Benford helps in the sense that it makes disappear that false solution that we found by counting the zeros, the rightmost zeros, which was, you can think of it as a local minimum. It's not a very good image because we're in high dimension, but it's like a local minimum where all the models are stuck. They found a cheap solution, cheap and good enough solution, and never get out of it. Apparently, the change of distribution helps to get out of it. But what exactly is learned in the Benford case is still, I'm working on it. This is something I don't understand. And it's not something simple, at least.
So maybe a more general question for both of you that relates to a question I asked before. What do you think are the most likely categories of methods that are likely to succeed for, regardless of what we can do today, for helping with mathematical reasoning, basically with AI? So at the moment, what's missing, from current AI systems essentially is the ability to plan in a general case and sort of reason with a limited number of steps, the way humans do. We don't spend a fixed amount of time for every problem, the way LLMs do, for example. So, what are the sort of main limitations? Perhaps related to the question of mathematical intuition, the fact that when we do mathematics and certainly physics, we have a mental model in our head. I think this was mentioned in the introduction or in one of the previous talks on I think it's Moshe maybe who mentioned this, that manipulating, having an intuition of geometry in the three-dimensional world allowed us to kind of derive more general properties about vector spaces and in infinite dimension and things like this, right? So or higher dimensional space and sort of non-Euclidean geometry. So how do we get machines to reason and plan, first of all, which is an important problem, not just for mathematics, but also for general reasoning, for code generation, for just about anything. And how do we get them to learn mental model and kind of reason with them? Go ahead, Adam.
I can maybe give like a mathematician's point of view on this question. So, as you said, planning is the one thing that's definitely missing. And also, whenever I write a proof, I always have these two images in my head. So I have a global picture, which is a rough overview of the entire proof landscape that I'm in, entire proof attempt that I'm doing. And I'm constantly searching the space, what overall proof attempts are most likely to succeed. And to be able to search in this space, I need to have some kind of black box in my head, some intuition box that I can always ask, is this global proof attempt more likely than this, or which one is better? And I also have some kind of planning on a local level, but I'm thinking, what are the next small steps I should take? Should I use this and this and this idea? Will it put me in a better position in the proof or not? So the important thing is that I need to be able to search in both of these spaces at the same time, or going back and forth. And in order to do this, I do rely on this black box, the fact that I've seen thousands and thousands of proofs, and I know roughly what are typical good ideas in these situations. And if I apply certain techniques, what kind of position will I find myself in, just very roughly. So having these, some kind of architecture that I have no idea what it could be, is going to be the crucial thing.
Yeah, but the thing is, you said thousands of proofs. Humans see a incredibly small number of proofs, to be able to formulate new proofs, and in terms of language, even right, children are exposed to a very, very small amount of speech or language before they can manipulate it and even learn, basic things about the world, compared to LLM. Typical LLM today is trained with something between 1 and 2 trillion tokens, which would take on the order of 20,000 years for a human to read, at normal speed, 8 hours a day, right? So the amount of data that we need to train the system is just gigantic compared to what humans can get away with. We learn to drive a car in about 20 hours of practice, and we still don't have level 5 autonomous driving, even with tens of thousands of training data from experts. So obviously, we're missing something big with our AI systems today that allows humans and animals to learn really quick that our current AI systems do not have the ability to do. François, do you have a comment on this?
Can I very quickly reply to the driving thing?
Sure, go ahead.
Just very briefly. So I think we are lucky that in mathematics we don't have this issue as in AGI, where all these large language models can only interact with us with text, whereas we humans have all these other stances. So luckily in mathematics, we only have text, like we humans also interact with it with text. So we don't have a disadvantage. So that's why I'm optimistic that mathematics will be easier than all the self-driving car things.
François?
Sorry, two things. If we talk about proving and improving concepts and reasoning, I think at one moment, one thing that was never considered or never considered enough in the past attempts is how do you define concepts? How do you define, part of proving is finding the right definition. And as mathematician, when learning mathematics, I'm not a mathematician, you have very early good idea of what's a good and a bad definition. What's a theorem and what's a lemma, what's a corollary, and all that. And this makes sense, and you don't need a lot of examples. So maybe, kind of training a machine that is able to maybe decide what's important and what is not, maybe decide what needs to be proved and what's not, maybe define, add definition and add working definition or working lemma and all that would be a good step. So we're sort of at the, producing concept levels. That would make sense. If you think out of proving in the broader schema, broader pattern, I would tend to say that there's a lot of things to do with the generative models, because generative models can really support and help intuition. Basically, once you've learned the right representation, again, it's concept building. But when you have a problem, you learn the right representation for this problem from lots of examples that you've built one way or the other. And then out of these examples, using the same kind of diffusion methods you use for image or whatever, you end up producing, likely or possible or interesting solution. You need to test that, but I think this is a sensible and relatively short-term ideas because, all the other guys in AI have done the work for us. They've done it for images. They know how to do it. There's a lot of things that have been already done. One last thing I've been talking about, we've been discussing that with Stan Dehaene recently, is that it's something about mathematics. When you learn mathematics as a child, something that is strange is that many of the concepts don't surprise you. You're not surprised at the idea of a square, a line, a triangle, even though the world is not full of squares, lines, and triangles. So we somehow learn a couple of intuitive mathematical concepts from, the real world. So shouldn't we add some kind of, I don't know what it should be, but real world elements to mathematical training or pre-training of transformers? We train transformer on figures, on geometric figures and all that. So I know some people have tried that, but this would be a next step I would be very interested to push, because I think there can be lots of gains just by that, by improving the concept building thing and the representation.
And I believe Stanislas Dehaene, whom you mentioned, is speaking in the workshop in the program. Yeah, he studies the acquisition of mathematical concepts in children, among many other things. So one characteristic, though, and this was in a question from the audience that disappeared, but the fact that generally when we try to prove something, we come up with a sketch of a proof, which is sort of a high-level abstract approximate representation of that proof that we imagine will take us to where we want, right? So maybe that's using this manipulation of our mental model of what the mathematical object we're manipulating is. And then we sort of refine that proof, right? We decompose it into kind of steps, and then finally kind of turn it into sort of formal symbols on a page. But it seems to be this sort of hierarchical top-down process by which we, plan in general terms and then sort of refine the process and try to kind of, make all the steps fit with each other. So this notion of hierarchical planning is completely unsolved in the context of AI. The only cases where we have AI systems that can do hierarchical planning, the levels, the representations at the various levels are hardwired. So, for example, if you want to get a walking robot to go from one point to another in a room or a house or an environment, you do hierarchical planning in the sense that you first plan a generic trajectory that gets around the main obstacles, and then you send that to sort of a lower level planner that figures out like what movement of legs or whatever are necessary for that, or kind of low level actions. But what we would be talking about here is a system that can actually learn hierarchical representations that would allow it to do this hierarchical planning. And nobody knows how to do this. Is there any hope we'll ever get there?
So one thing I doubt is, I'm not absolutely sure the hierarchical planning is so necessary. I mean, it might just result from the fact that we are extremely bad at, any kind of high dimensional reasoning or anything that takes a very large amount of working memory. So we like to split things into parts. But
well, that's why we are bad at chess and Go, because chess and Go do not require hierarchical planning, but they require a lot of memory and speed. That's what humans don't have. But that's why those games are hard for humans and easy for machines, right?
Yeah, true. But again, the neural nets live in a very high dimensional place where we don't have the same exactly intuition. So it's quite possible that the hierarchical planning is less necessary than we think once you have the capacity of living in high dimension that neural nets have. On the other hand, there's another interesting question. If you want to do that relates to the things you mentioned a while ago of having an LLM that works with a machine. And there's a metaphor I heard 2 days ago, which was comparing the center and the minotaur. So the center, it's a human head on top of an animal. And so you have the machine, the animal, doing all the hard work, and the human thinking over it. So basically you delegate the thinking to the machine. The minotaur is the opposite, it's a human legs and arms with a machine or an animal head. So if we want to do hierarchical planning, which model do you want? Do we want to have the model, so the AI working as the brain and dedicated system, classical system working as the legs, or the other way around? And it's absolutely not clear. We might want to delegate the hierarchical part to some kind of automatic planner, and then have kind of a gradient-based thing to learn the basic tasks. So it's very difficult to understand, exactly what we want in terms of hierarchical planning, because I think we're extremely influenced by our own limitations that create the necessity of hierarchical planning.
Okay, we're out of time. Adam, do you have a last short comment, perhaps? Okay, thank you both so much for this session, which was very interesting. And I think now we have a break.
Record. Hi, everyone. So it's 1 p.m. Eastern, so we are going to resume the workshop. I just want to remind everyone that we're using Slido to field your questions. So if you would like to send in questions to the speakers and panelists, please go ahead and go to slido.com and type in AI for Math 23. And with that, I will turn it to Talia, who is moderating the next session.
Thank you. Welcome back, everyone. So my name is Talia Ringer. I'm an assistant professor at UIUC, and I work on tools that make it easier to develop and maintain formally verified software systems. So I'll be moderating this next session, which is on case studies in proof verification and checking. So we have 3 really great speakers in this session. So our first speaker today is going to be Terry Coquand, who will talk about interactive proof assistance. So Terry Coquand is a professor in the Computer Science and Engineering Department at University of Gothenburg. His research interests consist of type theory, proof theory, interactive proof assistance, functional programming, and constructive mathematics. So Terry's type theory work is actually at the foundations of some of the most widely used proof assistants. So we're kind of fortunate to have him here talking about proof assistance. So take it away.
Okay. Thank you. So I will try to share the screen. So can you see? Can you see it?
Yes, looks good.
Yes.
Yeah, good. This talk will be a very general introduction to the field of interactive proof assistant. So there will be more details in the talk of Greg and for computer science and Johan for mathematics. So the content will be the following. So first, I will try to explain why is it possible to check mathematical correctness of mathematical proofs using computers. And then, so it is possible, but why is it interesting? And then finally, how does it look like? So why is it possible and how is it possible? So it's because of the special status of mathematical science with respect to correctness. So in all other field of knowledge, I mean, if you want to know that something, so for instance, you ask a question to ChatGPT, you get an answer. So if you want to know if it is correct or not, so outside mathematics, you have to rely on an external authority. I mean, you have to check on using Wikipedia, for instance. But in mathematics, the situation is different. So there is an objective and a purely internal way to ensure correctness of a mathematical argument. And this is because, so the checking of a mathematical argument can be done using only the form of the argument and not the content of the argument. So the fact that logical reasoning could be recognized correct only by the form and not the content, so it's quite old. So it's a key insight of Aristotle, who formulated the formal rules for logical reasoning. But the fact that it was possible to express such formal rules for mathematics so is more recent. And so it was one main step actually was the work of Frege, was possible to refine the formal rules of Aristotle and make it more complete and make it actually complete so that you can express mathematics using this formal system. So, and there have been refinement. So during this point, so it has been possible actually to check mathematics in a purely formal way. So that means it's possible to check correctness of mathematics in particular, so using computers. So this doesn't mean that so intuitions, social aspects don't play a crucial role in mathematics. So fully intuitions so will be covered by AI. But at the end, so for in mathematics, so a mathematical argument is only accepted if it is formally correct through this objective process that has been slowly made explicit. And so because of this, so a natural goal for mathematicians so is to use those formal rules to express mathematics. Before the use of the advent of computer, I mean, this goal was considered to be completely unfeasible. So for instance, So this was discussed by the group Bourbaki, who attempted to have a presentation of mathematics as completely precise as possible. But for them, I mean, this goal was unfeasible. But the situation has completely changed. So with computers, so because of computers, so they can do checking formally without problems, and it is not possible so to write even complex proofs in complete details using so interactive proof assistance. So this is so in theory. Why is it interesting? One general answer is that one can say it's a direction of history in mathematics. I mean, towards more and more precision in expressing proofs. But there are other motivations. Some of them come from computer science. So for the software correctness, so some proofs in computer science are simply too long, too complex to be sure of all details if you do the proof using only pencil and paper. And for some applications, so to have all details correct is essential. So I will give 2 examples. There will be more in Greg's talk. The first one is Silva, so which is an operating system microkernel that has been completely formally checked, proven correct, so bug-free against its specification. And the second example, so it's Koumoutsakos, which is a formally verified C compiler. And so this is nice because you get guarantee of security, but also because you have this formal verification actually for when you want to apply this in some special applications where correctness is essential. I mean, you can use, you can do optimizations. You can start to prove correctness of those optimizations, and you can use those optimization in a safe way, which is very nice because you get actually more efficient programs. So you get guarantee both of correctness, but also of efficiency. So those are actually strong motivations from the field of computer science for the use of interactive proof assistant. In mathematics, you can ask, I mean, is it interesting to have interactive proof assistant in mathematics? So surprisingly, maybe, so the situation is a little similar. So in the past 50 years, there are more and more actually proofs in mathematics that are too complex, simply too complex to do checking by hand. So the first example of this kind of proof was a result in group theory. So this Fate-Thompson theorem that that was proven in the 60s, and the proof took 250 pages. And when you have such a result in mathematics, so how do you check the correctness usually? Well, you organize a seminar. So you meet every week and you try to discuss the proof until you have checked all details. And for long proofs, so it can take several weeks or several months. And for this example, actually, so a colleague of Jean-Pierre Serre, so who was a specialist group theory, so Claude Chevalet, tried to organize such a seminar for checking this proof. But this took 2 years, and after 2 years, actually, they were not able to check the proof. So they stopped, simply because it was not feasible to do checking in this way. And the situation, as Jean-Pierre Serre expresses, is not very comfortable in mathematics. You want to be sure of the proof. Another example, so it's in some field of mathematics, in topology, where you use intuitions, and only experts can check the correctness of the proof. So this is not satisfactory because this relies on experts. And for the next generations, if you don't have this expertise, then you are not able anymore to check the proof, and you have lost this cumulative aspect of science, which is really nice and that one wants to keep. So all those problems so disappear with the use of proof assistant. So complex mathematical proofs, such as the ones that I mentioned in the previous slides, Fate-Thompson theorem, or some examples also in differential topology, are now checked in complete details with the help of interactive proof assistant. So this is also motivation for the use of interactive proof assistants. But another use, which is maybe more interesting for some mathematicians, is that those tools, hopefully, so they help mathematicians in getting a better understanding of proofs. And that's really the goal of mathematics. You want to get to understand better the situations, and these tools can help. So one goal is to produce actually better proofs, and I hope Johan will say more about this in his talk. Another motivation, so that is directly interesting for me, is that when you try to represent proofs on a computer, you try to think about, the fundamental question is how to express formal rules for mathematics. So a nice example of this was the example of equality, notion of equality in mathematics, which is one of the most basic notions in mathematics. So there were new insights about the logical rules of equality that were discovered with unexpected connections with the field of homotopy theory. And for this, so the use of proof assistant actually played an important role. So that's another motivation for studying proof assistant. So we've seen some motivations for the use of proof assistant. So how does it look like to use a proof assistant? So development of proofs have a very strong analogy actually with the development of programs. So there are the same issues of modularity when we have large proofs, such as the proof of this theorem in group theory, Fett-Thompson theorem, and what you have to do when you develop a large software. So there are the same issues of notations, same issues of choice of names, same issues of maintenance. So you do a proof using one system, and then the system evolves, and then this proof cannot be checked in the next version of the system. So, this is problem that you have in software that you also have in proof assistant. So there is this notion of program repair, and similarly, so there is the notion of proof repair. And another aspect of proof assistant is that most development are teamwork, so like for large software development. And this collaborative aspect was especially stressed by the late mathematician Wojewoski. So this is one nice also aspect of this use of interactive proof assistant. So in informal mathematics, when you rely on a result of a colleague, you take risk. So it happens that you start from the result of a colleague, and then you invest a lot of time and energy, and that at the end you think using this you have been able to solve an open problem, only to discover at this point that actually this result was not completely proved, or even was wrong. And this happens, and this is also an obstacle to collaboration in mathematics. And hopefully, so with the use of proof assistants, you will have more collaborations between mathematicians, because once a result has been formally checked, it's you are sure of the correctness of it. So another aspect of the use of interactive proof assistant, it's also this interactive aspect. Get immediate feedback when your attempt of a proof is not correct. Okay. And because of this, so several actually users of proof assistant pointed out an analogy with video games. There is the same feeling when you do a proof using the system as video games. So this is nicely expressed by this quote of Tobias Nipkow. So because of this immediate feedback, actually these incorrect proofs are rejected. And this can be actually a motivation for some motivated students. So they take this as a challenge, and they will persist and they struggle to convince the mathematics that indeed the proof is correct. So to be concrete, actually, I wanted to give a live demo of how it is to use a proof assistant. So I will stop sharing and do an example of a formal proof to show to you how it looks like. So this is, so do you see the screen? Yes?
Yes.
So yes, thanks. So this is an example, so done in the proof assistant, so Lean, and this is really presented as a game. So, but instead of being a video game, So this is a game about learning about natural numbers and how to do proof by induction. And like a game, a video game, so you have different worlds, and each world has several levels, and you can go to the next level. You are supposed to go to the next level only if you have solved previous levels. So let's take an example of a world. So this is the world of functions. And so you see, you have different levels like this. And in this example of function world, so that's an example of a goal that you can solve using a proof assistant. And this goal, so here is presented as in a diagrammatic way. You have mathematical functions given by this diagram. And your goal is given an element in P in this set here to produce an element in the set U. You see, it's very simple if you have this diagram, okay, this intuition. So you simply follow this path, actually. So it's more problematic if the problem is given to you in this logical form. So here is the goal. So there are all the hypotheses that you have, so all the functions. And the goal is to build this goal, so to build an element of U given all these data. So this example is interesting because it's very simple, but it's an example of actually how you, how different is the difficulty of the problem when it's presented in this intuitive form or in this logical form. But these two forms are actually isomorphic. So we want to be able to transport one problem into the other. But that's not what we are going to do here. So how to solve this goal? So you solve it by interacting with the computer. So so for instance, so you want to solve this problem there. So you see that well, simple. You want to use the function L to solve these problems to reduce the problem from U to T. So you ask the system to apply this function L. And then the system, sees that when you do that, then you are reduced to the problem T, simply T. Okay, so now you have to solve a problem of building an element in T, so that's simpler. So how to build this element? So you use these functions from Q to T. So, but if you make a mistake in your interaction, so for instance, you say apply L again, so the system will complain. So it will say there is an error. It's invalid. You cannot use this function L to reduce T to something simpler. So you go back and you say, well, yes, I see now I want to use this command J instead. And now you are reduced to solve this problem Q. So now it's simple enough. To produce an element Q, in Q, you simply apply function. So you apply the function H to P. So you can give the answer directly, so that this exact command. And then the system is satisfied, so the proof is complete, and you can go to the next level. So this is how it looks like to interact with such systems. So you see, it has some similarity with games. And Johan will probably present a more complex example. So to finish this presentation, so I want to say some word about so what we can hope from AI. So this interactive proof system, so it deals with correctness of mathematical arguments. So for some mathematicians, so correctness, it's the less important aspect of mathematics. This is essential, but mathematics is really about understanding. Okay, but at least correctness can be precisely defined and done in a computer. So correctness, but expect from AI are two things. So first, as part of AI, so there are some automatic tools like SAT solver, so SMT solver, model checking, that are really useful for interactive proving. And they are useful also in abstract part of mathematics. So for instance, for this proof of Fate Thompson, at some point for proving some lemma, Georges Gontier realized that, well, this problem actually can be solved by SMT solver. And so he wrote in the proof assistant itself, so which is similar to a programming language, he wrote a simple SMT solver that was able to solve the lemma. And it would have been very difficult to solve it by using this kind of interaction. So the use of these tools are really important for some lemmas in mathematics. But what one expects from AI is so this aspect, this creativity, that's really important in mathematics. And so one remark is that so often creativity is best expressed when you have against constraint and rigid framework. So if you are not too free, it's not so easy to be creative. And at least so these interactive proof assistants, so they can provide this rigid framework in which you can try to be creative. And finally, so as I said, so this aspect, this use of interactive theorem prover, so it looks like games, like a game activity. So AI can be so incredibly good for some games, like the game of chess. So why not in the game of proving mathematical theorems? And I will end by this question. Okay, thank you.
Awesome, thank you so much. So we will have the Q&A at the end. I do have a quick question I want to ask just for clarification before I move to the next speaker. Mostly because I think this is probably the first time a lot of people have seen these proof assistants. So one thing that comes up a lot when I'm showing these teaching students how to use proof assistants is why we should trust them to begin with. Like what actually is it that gives us confidence that when a proof assistant checks our proof, it actually proves the theorem we've set out to prove and it doesn't have any mistakes. So I'm curious if you can just touch on that quickly.
Yeah, so very quickly. So I said, so the mathematicians have came out with this set of formal rules so that are enough to express mathematical proofs and also enough to, if you use them in a correct way, you are sure of the correctness of what you are doing. And this set of formal rules is surprisingly small. So that's why, if you use only this small set of rules, you are safe. That's a short answer. Okay.
Awesome, thank you. All right, so our next speaker is Johan Commelin, who will talk about interactive theorem proving using these proof assistants. So Johan is a postdoctoral scholar at the University of Freiburg. His main interest lies in algebraic geometry, algebraic number theory, and formalization of mathematics. Johan is also one of the maintainers of the mathematical library for the lean theorem prover, which you just saw a little bit in the previous talk. So take it away, Johan.
Yeah, thank you so much. Let me share my screen. Yeah, thanks for organizing this workshop and giving me the opportunity to speak here. So today I want to talk about basically four things. First of all, a very quick overview of interactive theorem proving. We saw some of that in the last talk. And then I want to talk about desired features of formal proofs from three perspectives, namely the perspective of readers, of authors, and of maintainers. Then I want to give an overview of the state of the art of automation for formal theorem proving. And finally, some futuristic thoughts about how ITPs and AIs for mathematics can enhance each other in both directions. So let's get started. There are three components, roughly speaking, to interactive theorem proving. There's this formal verification where you mechanically verify this small set of logical rules. You mechanically verify proofs using this small set of formal rules that Thierry Coquand talked about just now. Then there is proof automation, because you don't want to apply all these small rules all the time yourself. So you would like the computer to sometimes help you and assemble them. And this can be done using traditional symbolic methods or neural networks or combinations of those. And then there's libraries, which are often neglected, I think. But to do like large and exciting and new and advanced mathematical projects, you need large and well-designed libraries that underpin these projects. Okay, so let's dive into what an interactive theorem prover looks like. So here we're looking at the Lean theorem prover running behind the VS Code code editor. And this is the file in which the main result of the liquid tensor experiment is formally verified. And so this liquid tensor experiment came about as a sort of serendipitous event where Peter Schulze about 3-4 years ago proved a very fundamental result in he has a new approach together with Dustin Clausen to complex geometry, and they're completely redesigning the field and reproving all sorts of theorems, classical theorems, using completely new proofs that are much more sort of conceptual, and they reduced to one big black box result that was proven around 2019. But Schulze wasn't completely sure about that part of the proof of that theorem, and it was extremely complex, and he didn't really see other people vetting it either. And he was afraid that people would rely on his prominence as a field medalist and just believe the theorem for that reason. So he challenged people in the formal verification communities to verify that theorem. And I followed up on that challenge with a group of about 15 people. And 2 years later, we completed the experiment and formally verified the entire proof down to the axioms. So, and as a result, we also simplified some parts of the proof, and Schulze himself says that he acquired a better understanding of the mathematics of the proof through this process of like interacting with the people who were working on the formalization, etc. So what you see here, there are two panes. So there's the input window where code is written, and then on the right-hand side, there is this goal state. So the highlighted line is where the cursor is, and it shows you exactly which assumptions are in place at that point in time and what the goal is that you need to prove. And so you can use that to decide what to do next. Okay, and yeah, so interactively build up a proof of the theorem. So at the top of the file, we import some prerequisites from the library. So this makes this point that you don't want standalone files. It's part of a huge project. And well, you can put some global assumptions in place. Then we have a theorem statement about profinite sets and p-Banach spaces and X groups, whatever that are. And then finally, we have these tactics that build up the proof. And these tactics are tiny little lean programs that, or sometimes they're large programs that build up the proof for you. Yeah. Okay, and then so we're building on this library, and so I'm one of the roughly 25 maintainers of MathLib, which is a library of formalized mathematics in the Lean theorem prover, comprising over 1 million lines of code. And you see some statistics, so there's over 300 contributors. And it's important that these libraries are like actively designed and maintained so that you have a part about groups and a part about topological spaces, and they work well together when you want to work with topological groups. Okay, so this is what I wanted to say about this interactive theorem provers, and I claim that they form a rigorous and precise platform that, well, now and in the future can be used, well, first of all, of course, to verify correctness of proofs, and they can give interactive feedback in education. Those are maybe two obvious points, but also, well, this interaction with proof automation, they are a perfect platform for both symbolic and neural methods in proof automation. And they can be sort of a common place where you can also have interaction with computer algebra systems. And I think they're a perfect tool for mathematical knowledge management to organize and preserve and the mathematical corpus that we have and to search through it. Okay, so desiderata of formal proofs. As a reader of formal proofs, I want them to be readable So that means that there is good notation and good documentation, and that I can explore them interactively. And I want to be able to answer questions such as, what is the main idea in this proof? And which assumptions do I need exactly to apply this result? And maybe I want to see where a certain hypothesis is used. And so I think some exciting work recently is that Patrick Massot and Carl Miller have created a tool that takes a lean proof, such as the one you saw, and turns it into a website where on the left-hand side you have a proof that looks almost like an ordinary English language proof written in LaTeX, but it's created from the lean code, and you can click on these little ovals and it will give you the current proof state on the right-hand side, as you have in lean, but now in sort of English language. You can hover over an assumption and it will tell you exactly which assumption is being used and things like that. And you can expand and collapse parts of the proof using these plus symbols. So if you want to see this interactively, you can go to this URL and play with it. As an author of formal proofs, I want a system that is extremely flexible, powerful, and expressive, and that means flexible and expressive foundations, but also flexible input and output. I want interactive diagrams that I can move around and play with, and I want the notation that mimics what we do on paper. I want a large library of preliminary results, and this somehow has to be built. And I would want automation that is, first of all, fast, second, effective, and third, it should be well integrated into my workflow. And ideally, I would just want to sketch the main ideas of my proof and leave the rest to automation. And most of this is like extremely futuristic at the moment and doesn't really exist yet, but maybe AI can help. And as an author of a proof, sort of selfishly, I just say a proof is a proof, and I don't care how we get there. I just want to know that the result is true. Of course, there's a tension with what I want as a reader, but I'll leave that tension in place for now. And finally, as a maintainer, I'm one of the maintainers of this huge library. I want proofs that are robust and deterministic, and they should also be fast, because if you want to check more than 1 million lines of code, you don't want to wait all day. And yeah, we have like more than several tens of editions a day. So and every time this library has to be checked. So it needs to be fast. And we don't suddenly want proofs to break, so they should be deterministic. We also need to refactor the library sometimes, and so we want tools that help us do that. If some lemma name changes, well, it should be automatically updated everywhere. And if somehow, for some reason, a lemma is generalized and some proofs are broken because they don't understand how to generalize their assumptions or something, then we would like to have automation that fix those broken proofs. And we would run tools that guarantee the quality of contributions to the library and just of the library as a whole, using things like linters, tests, and continuous integration. And so there's a tension between these 3 points of view. Yeah, maybe AI can help to maneuver between them. Okay, so automation and the state of the art of automation for ITPs. So first of all, there are decision procedures. And so the idea is that, as we saw in the talk by Morrisett, that certain fragments of mathematics can be decided by algorithms, even though not all of mathematics is decidable. So an example is Euclidean geometry. If you have a Euclidean geometry problem, for example, some sort of geometry problem on IMO, then you can just feed it to a certain algorithm and it will say, yes, this result is true, and it will spit out a proof for you. So these tools are often very fast and powerful. They're deterministic, but they're limited in scope because they only work on a small fragment of mathematics. But within their scope, they're often used a lot. So another part of automation comes from connections with computer algebra. And the idea is, well, you take one of these fast algorithms in a computer algebra system, and you use it to do some calculation that is then easy to verify. For example, factoring numbers is really hard, but if some oracle provides you with a factorization, it's very easy to verify that it indeed is a factorization by just multiplying together the numbers. connections between ITPs and computer algebra systems are emerging, but so far there isn't really a systematic protocol or framework, and I think it would be very helpful if this would be created. Another option is set solvers and SMT solvers that have already been mentioned in one of the previous talks. So the idea is that you convert your problem into typically a very large formula of Boolean variables and connectives, and maybe using some extensions, you have real variables, etc., and then it becomes an SMT problem. And you solve this problem using specialized software. So a small example of a Boolean formula is something like this, and try to assign truth values to A, B, and C such that the whole formula is true. So these tools have been used to crack immense proofs, like 200 terabyte size proofs, as we saw with this Pythagorean triple problem. And I refer to the work by Marijn Heulen for more details. However, these tools apply to a specific flavor of maths, and it's not really clear how to generalize to, say, a typical problem in algebraic geometry. And these tools, they concoct their own proofs and then give some hints to an interactive theorem prover, but the interactive theorem prover will sort of have to reconstruct this proof, and that's typically quite a non-trivial problem. So a lot of engineering is involved there. And finally, there are these neural AIs. So the idea is that you take your problem, the goal that you would like to prove, together with all the assumptions, and you hand this to some neural network, and you hope for a valid response that it constitutes a proof of that goal. And for example, GPT Formal, GPTF, co-authored 37 PRs to MathLib that minimized existing proofs that were written by humans. So I think that's a nice small success story hinting at what could happen in the future. So it's really amazing when it works, and I think there are really promising developments. This draft sketch and proof paper was already mentioned. Unfortunately, there's not really any integrated tooling. And when you try to use these tools, the responses are quite slow and it's sort of hit or miss. And so if you have to wait 10 seconds for a response and there's a 10% chance that it gives you something useful back, then often it's just faster to write the proof by hand. That's the state of the art. This could very well change in a few months or a few years. Also, it depends on like massive compute, and it can't really run on consumer hardware right now. And I think there are some sociological and ecological questions that also come into play there. Okay. Then finally, I want to do a little bit of dreaming and wishful thinking about how ITPs and AIs can enhance each other when it comes to mathematics. So I should point out that most of this is really dreaming and wishful thinking, but I hope it materializes in the near future. So how can ITPs be enhanced by AI and automation? Well, they could help with proof discovery. They might also help with explaining and outlining existing formal proofs. I think it would be really great if, when I'm taking my project like the liquid tensor experiment and trying to move it to a newer version of MathLib, and suddenly a bunch of proofs broke because lemmas were moved to a different file, or they got a new name, or they were generalized, or something like that, that some form of automation, some form of AI could help me repair those proofs. Because typically only a few little changes have to be made, but figuring out what those changes are exactly is a tedious and annoying process. And I would love to have that automated. And then there is like library design. If you're designing a library or designing one of these bigger projects, then you spend, like what you see on GitHub is on the master branch is some sort of polished result, but you don't really spend a lot of time in a polished end result state. Most of the time you spend in like a broken state, and you're trying to make progress and fixing it. And so like working in these broken states is something that I think AIs aren't really designed for, because they usually look at like polished end results. Yeah, so I would love better automation and AI tooling there. Yeah, so I think ITPs and their libraries can provide a lot of training data for neural AIs. And I think to do that, we should really take advantage of all the intermediate goal states and proof terms and tactic scripts and everything that is available in these libraries. And I think we should even capture like live editing sessions instead of only these polished end results that you see on the master branch of a library, so that in the training data, AIs can see how humans are moving from a broken proof state to a working proof state. And I really want to encourage AI researchers to take a look at Lean 4. It's a brand new version of Lean, and it's an extremely fast and powerful programming language besides being an interactive theorem prover, and it exposes an enormous amount of its internal structure. I really think a lot more than other proof assistants do. And so I think it's a perfect place to get exceptional amounts of very useful data when it comes to interactive theorem proving and maths libraries. Yeah, and I think ITPs can also be a framework that forms a rigorous feedback loop for AIs. So as humans, we learn maths from thousands of mistakes that we make during hundreds of exercise classes. And we learn how to correct these mistakes via discussions with peers and feedback from teachers and teaching assistants, etc. And large language models at the moment, they basically only see finished, polished material when they're reading stuff from the archive or from Math Overflow, etc. It's usually sort of not the raw things that are written by humans, but it's a polished product. And so I think we should fine-tune LLMs in a feedback loop with an ITP that allows it to see that something is a mistake and get feedback immediately and try to improve and backtrack, etc., and teach them error recovery in a rigorous environment. And I think this is a plausible path to move them from a very rigorous, opportunistic, anything can go state to a more rigorous state, and then hopefully a post-rigorous state, to use the language of a famous blog post by Terence Tao. And finally, I would like to end with a challenge. So I challenge people to create an AI that reads through all of MathLib and picks out important and/or beautiful results, because I think this doing this is intimately connected to being able to create and discover proofs and provide meaningful assistance to mathematicians when they're working on mathematical research. So thanks for your attention.
Awesome. Thank you so much. Yeah, so I don't know, it was really interesting. It's interesting to see how much that kind of overlaps with my experiences in program verification so far. There are a couple of kind of clarifications on Slido that people can look for just on some earlier comments. So thanks to folks who have posted those. Please keep posting questions, which we'll get to in the Q&A after this next talk. And this next talk is our final talk of the session. It's by Greg Morrisett, who will talk about some challenges for computer science proofs. So Greg Morrisett is the Dean and Vice Provost of Cornell Tech, which is a New York City-based campus focused on graduate education that integrates technology, business, law, and design in service of economic impact and societal good. Professor Morrisett's research focuses on the application of programming language technology for building secure, reliable, and high-performance software systems. So go for it, Greg.
Thank you, Talia. It's hard to follow Thierry and Johan, but I'll try my best. Let me share my screen and try to put it. Can you folks see that?
Yes.
Nope.
Yep.
Okay, yeah, I just wanted to contrast a little bit with what Johan and Thierry were talking about in the context of constructing proofs in math versus computer science, and in particular in software security. So, I think one of the challenges that we have with software today, especially for safety or security critical software, is just that a small flaw can lead to a gaping hole for an attacker to drive a wedge into. And many of the problems are not caused by nefarious hackers sneaking code into systems, but rather everyday programmers that we trust and we love creating bugs in software that then bad guys take advantage of. So the hope for software verification is really, can we take systems and use this idea of a proof assistant to check that the proof, check a proof of correctness or a proof of safety or a proof of security, and have all the auditing done by a machine instead of a humans. Because today, when humans try to audit code by hand, they, hundreds of millions of lines of code, they can't do it right.
Greg, is there any way you can put your presentation in full screen?
Is it not in full screen?
No, I think we just see the slide view with the.
Let me try.
Okay.
Did that work?
That looks great. Yeah. Thank you.
Dual monitors. So a perfect example of yet another bug in software. Just kidding. But let me tell you a story about a piece of code that Google wanted to verify a few years ago. So this was maybe 10 years ago. And in the context of the Chrome web browser, Google wanted to provide a service for downloading and running native machine code in the context of the browser. And this was something called native client. This happens in a lot of contexts where you want to take some code that you don't necessarily trust and run it in some context. That context could be an operating system or a web browser or a database engine, and you just don't trust the code. So what Google wanted to do was to sandbox the code. So what does that mean? That means to prevent the code from reading, writing, or executing code outside of predefined data and code segments. So that would protect the integrity of the core web browser in this case, or as well as the confidentiality of hidden secrets like keys and this sort of thing. But it would also protect the browser from just being subverted in other ways, for example, to access your file system. So Google actually built a tool called Native Client, as I said, to do this. And this is a tool it was based on something called software fault isolation. And the idea is, instead of using the operating system or hardware or other mechanisms, but to have the code be self-policing. So the compiler in this case was modified to cause the code that was emitted to check every read, write, and jump to make sure that it was within the appropriate data segment. So that meant adding extra instructions to the code to do these extra checks. And adding those checks is actually kind of subtle. There's a pretty tricky invariant that you have to maintain. And it's even more subtle if you try to optimize away those checks, which you would like to do for performance reasons. So one way to gain trust in this whole system would be to prove the correctness of the compiler. So Thierry mentioned, for example, CompCert, which is a compiler that's been proven correct end to end. Here you would have to augment CompCert with tools to add these extra policing checks into the code and make sure that those are correct. But that's one possible way to do that. The problem with something like CompCert is you actually would have to ship the source code along with CompCert to check that the output was the output of that code run on the compiler. And at that point, there's no reason in having native code around. So instead, what Google did was built a checker, something that looked at the machine code to check that it had been properly instrumented to have this self-policing property. And the checker turns out to be much simpler and smaller. Google's was about 600 lines of code and was relatively easy to prove correct. That's the good news. The bad news is Google didn't prove it correct, and they ran a competition to see if bad guys could break this very security critical piece of code, because this was going to allow anybody in the world to give you a link and download code to run in the context of your browser. And the bad news is there were about 20 different teams that found bugs in that 600 lines of code. So it's somewhat surprising that something that small could have so many different kinds of bugs. So a group of students and I set out to build a formally verified checker for this software fault isolation tool. It actually, the process of formalizing it caused us to step back and think hard about the problem, because if you've ever tried to verify somebody's code, it's really hard to take existing code and verify it after the fact. It's usually much easier to construct the code and the proof of correctness hand in hand. So in this case, we did that. We started afresh, built a new checker. This checker was only about 80 lines of code instead of 600. So it was an order of magnitude smaller, and it was much easier to reason about and prove the correctness of. And we actually did that, and were able to show that modulo some assumptions, and there's always assumptions, the code was actually correct. So what did it mean, though, for this checker to be correct? It meant that if we took this binary code that somebody sent us, and we ran this check procedure on it, and that procedure returned true, then if we executed that code, it didn't violate our security policy, that sandbox policy that I mentioned earlier. The problem with proving a theorem like that is that you need a model for, in this case, not only the syntax of the code, but how to run the code, the semantics of the machine code. And if you know anything about real machines like the Intel x86, it has literally thousands of instructions, and most of them are actually pretty poorly specified in a manual that Intel and AMD and others put out. Furthermore, there's not a lot of consistency in terms of these machines. They're in the corner cases they disagree on from different implementations. So that's a big challenge. And for us, it turned out proving the correctness of this software, this 80 lines, wasn't the hard part. The hard part was actually building this model of machine code that we could use to reason about execution of the code. And we built a lot of tools to try to automate as much of that as we possibly could. For example, we built some tools to scrape the PDF Intel manual so that we could extract the syntax and some semantic things from the text of the manual, but it was largely a completely manual process to construct this model. And of course, if there's a bug in that model, there could be a bug in our proof. So this is sort of the first thing that is my experience of the difference between computer science software kinds of proofs like this and mathematical proofs. That often the proof itself is very straightforward. There are just lots and lots and lots of cases, so many cases that you don't want a human having to reason about them individually. It's very tedious, and you'd like to have a lot of automation in constructing the proof. Furthermore, the challenge is often not the proof, but the modeling of the environment, that the real world that you're connecting to, that is as much effort as it is the proof itself. And finally, it turned out to scale enough to thousands of instructions, each of which had a very complicated semantics. We had to, as I said, automate this proof. And the way we automated that was through a sort of reflection mechanism, where we constructed decision procedures and then proved the correctness of those decision procedures, and then used those decision procedures to not knock off lemmas and the argument. And that kind of automation is, again, something that's important. Not only does it have to support reflection like that, but it has to run reasonably quickly so that you can engage with the proof in a reasonable way. As Johan said, that if you have to wait 10 seconds and find out that it didn't work 10% except for 10% of the time, then it's not much use. You might as well do it by hand. So that's one example, is this software fault isolation. Here's another sort of more impressive story, not by me or my group, but rather by DARPA. So DARPA ran this program called HACMS, and the goal was to to take a drone like the two that you see here. One is a consumer grade drone aircraft, and the other is an actual military helicopter, and develop a software stack for them that would be bottom up, correct with respect to a set of security policies. And that's a tremendous challenge. It was a grand challenge for DARPA that they presented to the formal methods community. And it was really exciting to see that they were able to pull this off. So in essence, it was a clean slate software stack. I should say, when they took the original drone software and gave it to a red team, the red team broke it in about 3 minutes. It took them no time to find holes, many holes in the software stack that was being used for those drones. They built the researchers involved built a new clean slate software stack that included things like that SEL4 operating system that Thierry mentioned, that's been proven correct with respect to a functional specification. And they also included other things running on top of that, including the stability and altitude control, as you see here, and the GPS waypoint navigation, or at least a big chunk of it. And they proved a lot of system-wide properties, like the system was memory safe. Turns out about 70% of the bugs that manifest in software today are due to memory safety errors because of people incorrectly allocating free memory or moving beyond the edge of a particular object. They also proved that it ignored malformed messages, that it made sure everything was authenticated before it acted on it, and that the good messages would reach the controller unless, of course, there was something like a hardware failure. So these are not full correctness properties. These are rather system-wide properties that DARPA had identified as important for the safe operation of the drone. And what was remarkable is they gave this system to a red team again, really good hackers who are good at breaking things, and gave them the software, gave them all the documentation, gave them 3 months, and they were unable to find a hole in the software. So one of the experts labeled this the most secure unmanned aerial vehicle on the planet. So in some ways, that experiment shows that if you apply these methodologies to real systems, then it actually scales up and you can get systems that are resistant to attack and failure. But there are still many hard challenges here. Just to point out one, that SEL4 kernel is really simple. It's a single-threaded kernel, for example. It's not even multi-threaded. And it took 20 person years to prove it correct. Writing the kernel could be done in a relatively short period of time, but it took that particular correctness proof 20 person years. People working in parallel, a lot of hard work. And since then, there's been great advances. For example, Zheng Xiao out of Yale and his students built something called Certicos. And what was interesting about Certicos is it went down to about 20 person months to prove correctness. And the key mechanism for that was not surprisingly automation. It was rather new abstractions and new ways of thinking about how to structure the proof to make it simpler to do things in a modular bottom-up kind of fashion. Another challenge is, same thing with these drones, the model of the environment is perhaps the weakest link in the chain of reasoning. That to reason about the hardware, the controllers, the attitude, the GPS and so forth, is only as good, the proof is only as good as the models are faithful to the real world. And as I mentioned, the policies didn't really cover all the safety and security requirements. They were just the ones that DARPA felt were most important, and extending beyond those could be a real challenge. And finally, it turns out that drone might be using AI software itself, for example, to do imaging or navigation or other things. And how do we reason about that particular code? In this case, what they did was they isolated that code and had it running in a secure box. It was isolated the same way that the software fault isolation that I talked about before. So it couldn't affect other parts of the drone, but that didn't mean that it was actually functioning correctly. And reasoning about those kinds of systems is incredibly hard. So I guess the takeaway, all I wanted to really capture was a couple things. One is that software security, the value in formalization is that machines have the patience to do careful auditing that's important to do, where humans just don't have the patience. And there's just way too many cases that have to be checked, and no human wants to do that kind of boring work after the fact. Because these are not interesting proofs as you have in mathematics, but rather tedious and relatively boring. And that's only part of the effort in any kind of software verification task. Constructing and validating models is as much of a concern. For example, when we constructed that model of the x86, we spent a lot of time trying to validate that model by running test cases through it. Another issue is constructing decision procedures to try to get things to scale. And then, as Johan mentioned, with libraries, or as Thierry said, it's kind of like software. When things change, for example, when the software changes, or the compiler changes, or the hardware changes, you have to reflect those changes in the proofs, and then you have to update them and keep them consistent. And maintaining proof engineering, as we call it, is a serious effort and still an emerging discipline in my mind. With respect to AI in this context of software verification, some wish lists for me, and this really overlaps completely with what Johan said. The first thing I would love is a co-pilot for all of these proof assistants like Lean and Coq and so forth, including a much better support for synthesis. It's amazing to me how low level these proofs are. I mean, basic arithmetic is still painful in these kinds of proof systems. And part of this is that the decision procedures are not coordinated the way that they are, for example, in a SMT, a satisfiability modulo theories prover. Another thing that would be incredibly useful is tools for summarizing big proofs and navigating through them. When you jump into a big project, just understanding and navigating through it can be an incredibly hard task, and I think AI could help with that, especially when it comes to things like intelligent search. I find myself reproving lots of stupid little data structures and algorithms where I could use a library, but it's just more work to go off and find the library than it is to reconstruct my own. And that's sort of antithetical to software engineering or proof engineering, but is the reality. Other things that I would love to see more work on is finding invariance and strength induction hypotheses. That most of the automation works okay for these tools, but the creative parts in any of these proofs are really around finding the right lemmas, the right strength and induction hypotheses, this sort of thing, or finding the right definitions. And I haven't seen a whole lot of work in that context. There is a lot of work on transformations and refactorings. Talia's done some work on that. She could speak about that. It's interesting that a lot of times we construct proofs that are perfectly fine in theory, but in practice, it just takes too long to check them. And so we end up rewriting the proofs just to get proof checking time down to a reasonable amount of time. And that's true whether you're using a decision procedure like SAT or SMT, or whether you're using interactive tools like Lean and Coq. And then I would like to also see tools to help people generate real world models. So I mentioned constructing some half-baked tools to run through PDFs and extract from the English and other semi-formal text the model for this x86, but I think that's something that could be extremely useful in a lot of contexts. And then also synthesizing testing infrastructure to try to validate those models. So those are things that people typically don't think of, but are important when you have an overall verification goal. So that's all I have to say, and I'm happy to stop there, and I'll stop sharing.
Awesome. Thank you. Thanks to all of our speakers. So we're going to move to Q&A. We have about 15 minutes. So remember, you can ask questions on Slido. I'll look there.
Talia, I have a question.
Yeah.
Can I ask a question?
Sure, yeah.
So, Greg, I would be willing to bet that your models are not fully correct. I was involved in a project like that inside Intel, and we went to the book And we found out in many cases, like the book is not fully, the book is ambiguous. So we had to go to the people who write the code, who write the very low code to find out what do you actually do. And my conclusion is if you run experiment, you have to run two sorts of experiment, one on Intel machine, one on AMD machine, because it's not clear at all that you're going to get the same result.
It's worse than that. You have to run it on every revision of every Intel processor. Yeah. So we actually did a lot of non-determinism in our model to represent situations where either there was inconsistency or ambiguity in the specification. And so the model itself actually leveraged non-determinism a lot in order to over-approximate the potential behaviors of the machine. But I guarantee you're right that there's bugs in that model. And so constructing and validating, ideally, Intel would release a specification and they would follow the specification in the implementation and that we would all connect to it. And I think there's possibilities for things like RISC-V, which are more open in that context. But, like I said, after the fact modeling is part of the real world of dealing with systems, and we're always going to fall short on constructing those models.
But you're right about RISC-V, because the biggest issue, the big risk for Intel here, pun intended, are the gaps between the higher level and the microcode and the lower level. And what we have learned is that this open to side channel attacks. And to me, this whole 6 architecture in that sense it just cannot be fixed.
Yeah,
I think the gap is so large between x86, between the ISA and the actual code, what they have done all the years optimizing it to get efficiency, that I just don't see how they can make it secure.
Yeah, I think that's a really good point, that there are also different levels of fidelity in these models. Like in all the situations I was talking about, we were not really addressing timing or confidentiality. And so the models were just about functional correctness. And yet, if you needed to capture that level of detail, you would need much more refined models. And that's a tremendous challenge.
All right. So speaking of models, actually, this is a good segue to something I saw on the Slido. And this one's actually for Johan, but I think there's a way in which it kind of also applies to verification, which is, so Ernest Davis asked, how in practice do you verify that the formal statement of a definition or theorem in a library actually corresponds to the English statement?
Yeah, I think that's a really great question. And it's something that I couldn't really address in my talk. But suppose in some hypothetical world, we have a formal proof of Fermat's last theorem. Then this is sort of an almost straightforward thing to do. You have to check that the definition of the natural numbers in your theorem prover is correct, and the definition of addition, multiplication, and powers, etc. And then you could just compare the statement by hand with the usual statement. In the case of something like the liquid tensor experiment, this is completely impossible because recursively the definitions build on top of each other, and there are like 1,000 definitions that you would have to check. No kidding, like really more than 1,000. And so what we did was we sort of provided a whole bunch of examples of how you can use the formal definitions that we gave and showed that they can be used in statements that look very much like the corresponding English language statements. And this provides a sort of guarantee that we didn't make stupid mistakes while formalizing these definitions and statements. And so because Lean has a very expressive syntax, the statements are usually quite readable. And so this is a form of like abductive reasoning. There's the so-called duck test. If it walks like a duck and quacks like a duck and swims like a duck, then it probably is a duck. And I think you can use the same technique when trying to get confidence in the correctness of formal statements. So there is a blog post about how we did this on the weblog of the Lean Prover community. And I posted a link to it on Slido.
Awesome, thank you. So another question from Slido. So Terry, you kind of spoke about how this theorem proving the proof assistant is kind of game-like, which is something I've heard before. So Daniel Silag asks, there's a concern that this theorem proving game might be substantially more complex than any games we've previously solved. So one of the questions is is there anything that we can do to a proof assistant to kind of reduce the complexity of this game, maybe make it easier to automate?
I mean, that's a very difficult question. I mean, to prove mathematical theorem. I mean, mathematics is a very difficult game, and I don't think there are answer to this. Yes.
Does anyone else have thoughts on that too?
Well, in some ways, SAT and SMT are examples of that. Those are games that I think we could play.
That makes sense. Yeah, almost like any of these decision procedures is kind of like a game in a particular domain that you can decide. Yeah, cool. Let's see. I have a couple of general questions. So these are kind of for everyone. So all of you have substantial experience kind of writing these formal proofs. I'm really curious, if you could pick one thing that is just the hardest part of your formal proof development, what would that be, and how do you think better automation could help? Maybe we can start with Johan, if you have anything.
Yeah, I think for me the hardest part when working on like a huge project like the liquid tensor experiment is really sort of the global structure of the project and how to lay out the hierarchy of the project at large. And it's not really clear to me how AI could help there right now, but you could imagine something like the draft, sketch, and proof technique could help there. And so when it comes to sort of the most annoying or tedious things, which are in some sense also hard to do, I think it's really this proof repair where I think it should be possible to do something in the near future, because there is already like a proof that used to work, and now you just need to tweak it a little bit. And so there, I really hope that something like large language models could help. Yeah.
I find getting the definitions, the right definitions in place is the hardest part. And it feels like once you get the right definitions down, it kind of just flows.
Yeah, I think that's a really great point, because like on the one hand, there's a lot of like bottom-up development, but there's also a sort of a top-down approach where you say, okay, I have this concept, I don't have like pinned down an exact definition, but here's a bunch of properties that I want to satisfy. And at some point you would like to just sort of say, okay, now find the optimal definition that satisfies these properties. And the properties probably already pin it down quite a lot. But even if there are like 5 equivalent definitions, one of them might be a lot better for proving the properties than the other 4. And so, yeah, I agree. That's also a really great example. How easy it would be to get AI to help there, I don't know, but it would be lovely to have it.
Awesome. Terry, do you have anything to add?
No, I think also this point about definitions is, great. Yeah, and I have the same feeling.
Awesome. Yeah, and then sort of one more general question, building on that. So, I think probably in using these proof assistants, you've come across different kinds of automation. If you think about the proof automation that you actually use, versus the proof automation that, maybe you've heard of, maybe it sounds nice, but you've never used it and you wouldn't use it in your proof developments. What really makes the difference for you? And do you think there are any lessons for kind of adoption of this proof automation? So this is for everyone.
Yeah, I think integration into workflows, into like interactive development environments like VS Code, etc. That's extremely important. If there is a wonderful tool out there, but I don't have like a button I can click so that it runs on my current goal, or a tactic that I can call that does a query over the internet and sends my goal to something, like that, then I just don't use it. So integration and sort of UX, user experience design, that's just an extremely important aspect, which is a sort of an engineering aspect that I understand is not very exciting, but it's very crucial, I think. And the other aspect is, I think, this trade-off, like I'm willing to wait a long time if I sort of have the expectation that this is a powerful tool and it's most likely to give a helpful result. If it's extremely fast, then I'm willing to try it a lot of times, even though it usually doesn't return anything helpful. And there is a balance there. I don't know exactly what the balance is, but there's a threshold. And if you are above it, then I'll use the tool. And if you're below it, then I won't use the tool. I think those are two aspects that just apply to most tools and that make a huge difference in adoption.
Yeah, I've been very jealous of the SMT world because, well, at least when you read the paper, right? Like, okay, we proved this thing and it's completely automatic. What I don't know is what it's like really using these things in anger, because inevitably you get it wrong, you time out, the actual latency that it takes for it to come back with an answer matters, and then you kind of have to compile your problem into that fragment that it understands. So all those things do not show up in the final paper that says, oh, it's completely automatic. And so it's a little frustrating for me. Having said that, there's even more frustrating is in Cocker, and maybe Lean is better. The lack of integration between decision procedures means that, it's a combination of arithmetic and congruence closure and something, and I end up writing some manual tactic to sort of iterate on these things to try to get it to converge, and you just feel like there's got to be some base auto tactic that is fast and better than what we've got today, for the vast majority of simple reasoning.
Yeah, so if I may make a small plug for Lean, one thing that I really like about it is that it's very easy to write one-off tactics that combine a few other tactics. So yeah, that's one thing I like.
Thanks. Does anyone have anything to add to that? Okay. So I think on Slido, we have a lot more questions, but the speakers, especially Johan, has been doing a really good job of answering some of the smaller questions directly there. So you can also, some of the questions that weren't answered out loud, you can find things there, including like links to related work. So thanks for doing that. I think we should move to our next session at this point, as it looks like it starts in a minute. Is that correct? So our next session is, I have to find the part, okay. Yeah, so the next session is on the development of data sets specific to the mathematical sciences. This is moderated by Kavitha Srinivas. Yeah, and thanks again, everyone, and I will hand this off.
Hi, I'm Kavita Srinivas. Thanks, Talia, for the introduction. So this session will be about the development of data sets for mathematical sciences, and our speaker today is Sean Welleck from the University of Washington. Sean is a postdoctoral scholar at the University of Washington and is going to be joining the faculty at Carnegie Mellon University this fall. Sean's interests are in machine learning and natural language generation. Especially, he's also applied it in the space of mathematical sciences. And he's done some interesting work in terms of building data sets for mathematical sciences that I'm sure he's going to tell you about. So without further ado, Sean.
Okay, can you see my screen well? You can see my screen.
You can see it.
Hear me well? Okay. Yeah, so thanks so much for organizing this workshop and giving me the opportunity to speak at it. So today I'm going to talk about challenges and some new frontiers related to data in AI and mathematics. So as we've heard about at this workshop, it's kind of an exciting time at this intersection of AI and mathematics, be it new ways to learn and teach mathematics, new tools for research and discovery, and new tools for making sure that more complex math and even software is correct. And so today I'm going to focus on a subset of this intersection related to language models and mathematics. And so you've probably seen language models through tools like ChatGPT. And these kind of tools are starting to show some interesting capabilities. Like on the right here is a language model called Minerva, and it managed to produce a correct solution to this question from the Poland National Math Exam. And we've heard about some other interesting success cases today. And so in general, these models kind of give us a potentially flexible way for performing different sequence-to-sequence tasks. And so one goal is to see whether and how these tools might help us perform useful mathematical tasks. And so the unique thing about math is that there's this kind of spectrum of tasks we could consider studying with these models. So some of them are very formal, like proving a theorem in a formal proof assistant. And then some of them are more informal, like having a free-form conversation about some mathematical topic. And there's plenty of things kind of in between. So let me start with the formal. And as we heard in previous sessions, these interactive proof assistants are a really interesting potential area for AI and language models in particular. So in an interactive or formal proof assistant, we can write math in a sort of source code. So for instance, here we're trying to prove that 1 + 1 = 2. Then we can write a proof, and if it kind of compiles successfully, then we know that the proof is correct. And so as a result, this is a really exciting area for using these language models, since we can check whether things are correct or not. And so where does data come into play here? Well, the first thing to note is that these language models are often trained on massive amounts of data. So for instance, over 1 trillion tokens of general data from the web. But I kind of wanted to point out that a really exciting thing is that even very small amounts of this kind of expert created data can still have a large impact. So let me start with evaluating language models for formal theorem proving and talk about one of the most common benchmarks that's used called mini F2F. So mini F2F consists of 488 problem statements, and they're mainly from competitions like AMC or the International Math Olympiad. And so these problem statements were written in 4 different formal proof assistants. And you can see the authors of the paper here. And kind of relative to the size of general web data, this is fairly small, but it's been a kind of very effective way to measure and drive progress in neural theorem proving. So in particular, it gives us a really easy way to experiment with new algorithms and evaluate them in an objective way. And so an example is we kind of used mini F2F as while developing a new method called draft sketch prove. So this was a project that was part of a big collaboration with people from Cambridge, Washington, Meta, as well as Google. And the method uses a language model to translate an informal proof, so one that's written in LaTeX that you might find in a textbook, into a kind of sketch that then guides a formal prover. So I didn't put the details here, but if you're familiar with Isabelle and the sledgehammer automation tool, what we do is kind of translate the informal proof into some sketch, and then we have holes that are then filled in by this formal, sledgehammer tool. And so then at the end, we get a formal proof that we can check for correctness. And so from a data perspective, this involved two different things. So first, it was extending the data set to also have the informal LaTeX proofs for each problem. And then second, in this case, writing 20 different examples that kind of demonstrated going from an informal proof to a formal sketch. And so in some cases, we are able to kind of do new algorithmic development with a fairly small amount of kind of newly introduced expert-informed data. And so one challenge with this is kind of making sure that we don't have too narrow of a focus. So for example, maybe our small data only covers one type of problem domain. And here one kind of exciting thing is that we could see the scope of these different benchmarks expand as research kind of progresses in this area. So just to point out another example here, this is a really recent benchmark called ProofNet. And it kind of aims to provide some coverage of undergraduate level mathematics by kind of formalizing statements from different textbooks. And so some new frontiers are continuing to expand the problems and domains that are covered. A good starting point for this is interdisciplinary collaboration and through workshops like this one. So for example, I really like Johan and Greg's ideas earlier for areas where AI might help in interactive theorem provers, and they kind of go beyond just just actually proving the theorem. Then when we move to more informal tasks, the kind of important thing to keep in mind is that it becomes difficult to evaluate. And this affects the kind of iteration cycle that we have while developing the machine learning method. And in particular with math, it gets very difficult to evaluate things like correctness. And so this is actually really important for these language models because in general, we don't have guarantees on correctness. So for example, I asked this ChatGPT to prove why this claim was true. And it started off by saying that the statement is false, which is just not correct. And then later on, it said that -1 is greater than 0.29. And so it's definitely possible that someone's typing this into the kind of newer model and it does work with the newer model. But I think the important thing to keep in mind is that in general, these types of methods don't have the guarantees on correctness. And so one thing to do in more informal tasks is to actually do a potentially costly expert evaluation, or to have experts kind of interact with these systems. So as a case study a couple years ago, we were interested in whether these language models might be able to help a student when they're stuck in a proof. And so here it was an informal proof written in LaTeX. And so kind of as machine learning researchers, we had to collect a data set and formulate some proxy tasks for this higher level motivation. So we collected a data set of theorems and proofs from an online source called ProofWiki. Then we set up a task and some evaluation protocol. So we fine-tuned the best language models that we had available to us at the time on the data set, and then took about 200 held out theorems. And then given a theorem and some proof that was written so far, we had the model generate some next step in the proof. Then we actually set up a study involving 15 undergraduate, master's, and PhD students from the University of Washington, and built an interface and protocol for evaluating the proofs. I just wanted to call out, so Jiacheng Liu, who's a PhD student, did a lot of the heavy lifting for doing all this. He held an entire training session with the annotators, and then we had them evaluate whether a proof step is correct. We could also evaluate other things, like even if something isn't correct, whether the generated step is useful for trying to prove the theorem on their own. And then we also had the experts identify specific errors that the models were making. So from this, we got a data set of over 8,000 annotated proof steps. And then from this, we're able to see some interesting things. So first, these models were indeed capable of providing some correct and useful next step suggestions in our evaluation setting. And then importantly, it also showed kind of concrete weaknesses of these methods on things like derivations and longer proofs. And so I just wanted to point out some exciting work from other groups doing this with kind of the most recent models. So in particular, they're moving to a more free-form setting and an interactive setting. And you could take a look at this paper, which was just posted last week on arXiv. So then another option for building a data set is to transform some hard to evaluate problem into one that's easier to evaluate. So here, this was a project led by Swaroop Mishra and Matt Finlayson. And what we did is to look at a wide range of problem-solving data sets in the literature. These tend to be, potentially like less sophisticated mathematics, things like grade school math, kind of short linear algebra problems or competition problems. And we noticed that they could be unified in this common form, which is going from some problem statement to some Python program that you can then execute and check whether the answer is correct. And so this gives us some evidence that the model has produced valid reasoning. Of course, we would actually have to look at the program to really check it, but also lets us experiment with using different tools like Python libraries or built-in operations. And so moving forward, one thing to do is to keep exploring the interaction of these models with humans and other computational tools. And then an additional step would be to see if we could use these interactions and the resulting feedback to make the models more reliable or to expand their coverage. And then finally, many language model-based tools that we depend on do depend on closed data, or the model themselves are closed. And so this can be problematic because there's kind of a lot of science to be done on understanding the data that these models are trained on, determining which data helped in an expert domain like math, and ultimately developing the models further. So this could mean better raw performance on a benchmark. It could mean investigating robustness and more efficient models that can run on someone's laptop, and ultimately building new methods. And so one way to open up these new research directions is through open source. And so we have a really exciting ongoing project to build a large corpus, model suite, and evaluation harness for AI and mathematics. So the project is with Luther AI and with collaborators from many different institutions. It's led by John here. And we're trying to collect around 50 billion tokens of high quality, publicly available content like papers, code, and web data, train models on the data, and add various math-related tasks to Luther's platform for evaluating language models. And the cool thing is that the research itself is kind of done in the open, and so you can check out the progress or contribute yourself. And we really think that this could open up many different research directions and also new tools that people can use. And I can go into this more in the Q&A if there's interest. So I talked at a high level about 3 themes that are important to keep in mind when it comes to data for language models and mathematics. First, even small amounts of high quality data can have a large impact for evaluating or even developing new methods. Second, many tasks are hard to evaluate and benefit from interactivity or expert evaluation. And then finally, open data could really enable new science in AI and mathematics, and that's important for both understanding as well as new applications. And then just to add a personal note, I'll be starting as an assistant professor at CMU in January. So if any of these sound interesting to you, please do reach out, and thanks for your attention.
Thank you for a very interesting talk. I had a quick clarification question. When you talk about small data and large impact, I think what you did there was to leverage language models in combination with more symbolic systems to achieve the performance based on just a few problems. Are there specific techniques, do you think, that you can draw from that sort of experience? Is that sort of the way to go? And also notice that you're also trying to build language models specifically for math. So do you think that those are sort of, what are your thoughts on that?
Yeah, that's a great question. So yeah, on the topic of using the symbolic tools, so in the case of draft sketch proof, we did have this nice decomposition where the model was generating some things. Intuitively, we might view them as being kind of high level sketch, and then some lower level things were being done by the symbolic tool. And so, yeah, I think these language models offer some really exciting things for continuing to explore in that direction, where we might have really solid tools that have been developed and kind of generalize really well on one type of problem, and then the language model is almost using something that kind of calls that calls it. Yeah, I forgot the second part of the question.
I was asking if you think that development of language models specific to math will also help with the small data problem. Is that the hope?
Yeah, so then another really interesting thing with math and with other expert domains is that so there's been other work that's shown that if we just use the general domain data, then we can get better performance if we additionally add in some expert domain data. Now, this expert domain data can be fairly large, so something like 30 to 50 billion tokens. However, it might be things like archive papers, like code that's relevant to math, and so on. And so a really good example of this was the Minerva paper that I mentioned at the beginning of the talk. And so the hope here is that we still have the stage of massive training on internet scale data. Then we have this kind of expert corpus that then gives us better transfer for the really low resource settings.
There's a question on Slido that it was very popular, but it was addressed to Francois Charton's talk. But I think it might be relevant here, and I'm wondering if your thoughts on that issue. So that the question says, we know from his talk that data distribution matters, but in many mathematical problems, we have very scarce data. So the issue of generalization keeps coming up, right? How do we propose AI that will be relevant to mathematical topics with scarcity of data? Now, I think the issue is not so much like low resource, but also the distribution of the data itself.
Mm-hmm. Yeah, so there's a lot of interesting stuff to say here. So one is, just to start with, one is this idea of using different tools. So if we look at something like multiplication, then even with very large amounts of data, we can kind of get these models to fail in sometimes surprising ways. But for instance, if we train them on a large amount of data and then look at a problem size that's not in the data distribution, then their performance might start to trail off. And then if you think about like multiplication being embedded in a proof somewhere, then it might seem like we need just like tons of data. Whereas in some cases, we might be able to offload this harder to learn part to some external tool. Then the other that I think we're all trying to still understand is when we do this massive pre-training or some fine-tuning on some still relatively large expert corpus, how well the models are able to transfer with low amounts of data. And so like one way of thinking about what we did with Draft Sketch Proof is we are kind of training the model for a new task. And in that case, in our setting, it only required a relatively small amount of data. But yeah, the extent to yeah, I think that's something that we're still trying to figure out as we apply this to new tasks.
Okay, we have time for a few more questions. So one is from Heather Macbeth. She asked, having a system output a Python program is a clever way to incorporate external tools. How does this compare to the tool former approach?
Yeah, that's a great question. So here we were kind of focused on the, one focus was the data set part. So we noticed that these different tasks were either in different formats or had kind of natural language intermediate steps that you couldn't check. And so this was kind of collecting everything into this Python form. Now something like the tool former, I think would aim to kind of demonstrate how you would train a model to automatically use different tools. And so one such tool might be calling Python, another tool might be calling some retrieval mechanism.
Okay, one more question from Slido. This is from Patricio Gallardo. Question is, will it be better if the problem solver data set is focused more on a particular area, such as calculus or algebra? The proof strategies tend to be quite different from one another.
So the question is like, is it better to focus on one area?
Well, I think the question is whether we need data sets that allow the model to generalize across them, or is there sort of, are the data set, should each data set be rather focused? And then you can think of like multitask learning strategies to learn more general approaches to proving.
Yeah, I would say that, so I mean, I think both things are are good to have the targeted sets as well as larger ones. Maybe just to add some like personal perspective, like if the data set is has too much coverage, then it might be difficult to tell exactly where a model's failing. Whereas if we have a more targeted set, then it might identify like specific areas within a particular domain that the models aren't good at. And then sometimes we can also reason about the method itself and think about whether it's like specific to the data set or might be more generally applicable. But yeah, I think that's yeah, both are important. So the more targeted specific areas, as well as doing some more general evaluation.
Okay, I want to ask one more question, which is also on Slido. So the question is about whether we should build LLMs that basically transcribe natural language through the formal expressions that are understood by the theorem prover, which is kind of similar to what you did in the draft sketch proof idea, isn't it?
Yeah, so I think, so first, I think it's really like, yeah, these language models and the interactive proof assistance, even as just like a machine learning researcher is really exciting because we do have the opportunity to check correctness in some tasks. And then, yeah, like others have mentioned in the talks today, there's potentially a lot of different tasks that the language models might be useful for with the proof assistance. So in that sense, it's really fruitful. And then particularly this idea of going from the informal to the formal is again one area where these models might, yeah, where they might excel in the sense that like with a traditional tool, it might be more difficult to generate natural language, but that's what the language models are kind of designed for. And then mapping them into something that's checkable at the end kind of gets around the thing that the language models aren't good for, which is ensuring that what they produce is kind of valid and correct.
Okay, and I actually have a broader question, which is when you're building your model suite, are you targeting many different data sets and benchmarks like Big Bench? If so, like what's the scope? Where, you know, how can people get involved, I guess?
Yeah, so our goal with the evaluation set is to provide some coverage of the kind of current categories that have been looked into with language models and math. So we have kind of math word problems, things of that nature. We have informal theorem proving, formal theorem proving. Then we have kind of math related code generation tasks. And to at least get some minimal coverage of those different areas, and have a model that, you know, does reasonably on those areas. So then in order to do that, yeah, it involves like actually doing the implementation in this evaluation harness. And so we're keeping track of ideas to add in on the GitHub. And as more people join, we can add more ideas too, because we have a lot of them.
Are there specific areas that you think are pretty close to, you know, fruition? That is there like proof repair, I heard was mentioned earlier as a place where it would be really nice to have data sets because there's an immediate application that one can see. Are there specific areas like that that you can point to that aren't there yet? There are no data sets there, but would be nice to have in as part of this benchmark?
Yeah. So proof repair would be great to have. Another thing to note is the kind of splits that are used for data sets. So when we're training a model on a bunch of internet data, then there's the possibility that somewhere in there, there's similar problems. And so one way to mitigate this is to actually create a new data set that's kind of from the future with respect to the model. And kind of that's a large undertaking, but something that we're definitely interested in.
Okay. Let me just take a quick look at that I've covered everything. In terms of the data set development, there are some comments on Slido that talk about existing databases that I guess of proofs from Lean. Are you also including that in your suite that you're talking about right now?
So yeah, so I don't
There's
have
like
the Slido.
theorems and definitions in Lean's 100K plus database of proofs. Can they be used? Are they being targeted for use in the building the language model? Or do you think that that's something you're going to set aside for your data set development?
Yeah, so roughly speaking, we have a few different categories. So we have code that is filtered to be relevant for math. And so that's going to include a large subset of Lean. Then we have to consider the evaluation tasks and that there isn't overlap between those two. And then maybe the second category that's relevant would be kind of existing math data sets that have some training set. And so they're potentially, yeah, I'm not sure the specific one that was mentioned. There potentially that might, yeah, fit in there.
Okay, we have time for maybe one more question. This one was also from Slido, and it says, how would you build data sets that capture more back and forth reasoning? For example, first looking for patterns in small examples and then coming up with a conjecture or changing the proof strategies because the calculations won't work out.
Yeah. Yeah, so here I think the important thing to always remember is the difficulty of like that these things become expensive to collect. And so we have to come up with some clever way of collecting a sufficient amount of data and then having it be in a form where it's a good machine learning task. So I think like one idea that was mentioned, it might have been Johan, which was the idea of just like keeping track of edits that are made or interactions that people do when they're using these assistants. Potentially those might be useful for like inferring changes and then patterns from those changes. But yeah, I might need to think more about that one.
A bit like GitHub commits have been used to look at program repair.
Yeah, exactly.
Yeah. Okay. I guess there's this Slido. I'm just looking at Slido again to see if there are any more questions. I think that might be it. So you have only one more minute anyway. Thank you very much for your talk. It was really interesting.
Okay, thank you.
And Petros, we're going to pass it back to you for closing comments.
Hi, Michelle.
Hello.
I cannot. Now I can hear you. Yeah. Can you hear me?
Yes, we can hear you.
Okay. Thank you. Well, I hope this was exciting enough for everybody as it was for me. I don't have much to add other than renewing the appointment for tomorrow. Just a second. Can you hear me? Hello?
Yes, we can hear you.
Yeah, I don't know. I think I got disconnected. All I wanted to say is that I felt that this was a very exciting day, and I just want to renew the appointment for all of us for tomorrow, starting at 10 a.m. Eastern time. Thank you very much.